So in NRC, it is purely focused on route section of the enterprise infrastructure. Everything related to the routing, you will study here. Like we'll talk about routing protocols. We'll talk about basics of the routing. Then we'll talk about the routing protocols. Some routing protocols that we have already studied, such as OSPF, at least in basics. But other routing protocols that you might not have covered in CCNA, such as EIGRP, and the other one is BGP. These two things we will talk about in addition to the OSPF one. And then we are going to talk about like static routing. We will talk about IPv6, routing on IPv6 for all these protocols and everything. So this section is purely focused on routing. And when switching is no longer there in Cisco's curriculum. If I show you the CCNP track that Cisco has, just let me. From the Cisco's point of view, like CCNP content, it is not going to include any switching now. It is just, you see here. So from the CCNP Enterprise Training point of view, you see like you have to take 2 exams. This is one of the core exam that you have to take, which is they are calling as NCore. And then you have to take ENARSI, that is Implementing Cisco Enterprise Advanced Routing and Switching. There is no switching here. Okay, like there are 1, 2, 3, 4, 5, 6, 7 concentration exams, and none of these cover switching. So since we already talked about that, they are planning to move everything on the software defined, and their things are mostly on layer 3. So you will not even require switching that much. So switching part is going to be very limited now, limited to VLANs, port security and all those things. Trunks will not be required because the links between the switches is going to be a layer 3 link, routed links. So trunking and everything will not be required. It might be required when we have like ether channel bundling and everything, but otherwise it will not. So it will be mostly limited to only VLANs and basic port security and these things. So nothing on here includes switching. So we will be covering this, this. And then later on, just in case if you want to go for like, for example, software defined. So it is one of the SD-WAN. This is design, wired network, architect track. The architect track that earlier they had separately, now they have in the enterprise. So it is now, this is wired design, this is wireless design. Even the wireless section that was used to be like a dedicated track for Cisco certification, now it is included in the enterprise infrastructure. And this is implementing Cisco wireless network. This is more like wired network, routed network, and this is more like the wireless network. And then they have this automation thing. So there are total 7 concentration exams that you can choose from when you want to be a specialist in any of these. And you take any one of the exam from here and you take this core exam and you become CCNP. So in the 2 exams, yes. So you have to take this exam that is mandatory and core. And you have to take any of these 7. It is from the exam point of view, it is mostly MCQ. All the MCQ questions are there, multiple choice questions are there. There will not be any lab to do. No, it is there. From the exam point of view or from the content point of view? No, nothing. It is just MCQ, multiple choice questions, just like in the CCNA. Earlier in T-Shoot, we had a dedicated lab exam kind of thing, but nowadays it is not there. Just the CCI, yes, just there. And this core exam actually works as the written exam for CCI as well. So before you go there, you have to understand things from security track. You have to understand the things from wired, wireless, and everything. So they say if you want to go for this, cover these first. Then you will have a better understanding of core exam. So we are not going to focus on this one. Just keep in mind that if you are going to attempt the exam for CCNP level, you have to take this and you have to take any of these.
It doesn't matter what
you do first.
Yes.
It does not matter whichever you do first. You can do encore first, and then these you can take this exam first, then this.
But each exam is apart from the other.
It is like they all are individual exams, like they are not related to each other. But if you want to be a professional in the enterprise infrastructure track, this is what you should know. They say, like, if you want to handle an enterprise infrastructure network in modern day networks, so this is all that you should know. So we are going to focus on this section, that is implementing Cisco Enterprise Advanced Routing and Services. Okay, so if I click on that, this is exam code 300-410, and it is going to focus on these things: layer 3, pure routing, then VPN is a part of security, but we will be talking about VPN as per the content. Like we'll talk about GRE, we'll talk about DM VPN, we'll talk about IPsec. We'll talk about VPNs in general. Yeah, in general we will talk about, but when it comes to like in detailed knowledge, you can get that detailed knowledge in the security track. Then infrastructure security and infrastructure services. In the infrastructure security and services, you will mostly find the things such as DHCP, Telnet, SSH, SNMP, NetFlow. These are all going to come under the services section. And the security, like we have access list, prefix list, these security features that we have. Yeah. So all those things are going to come here, and the automation is the last section that you studied already in the CCNP, like scripting part a little bit. Now, so the exam topics, you click on here, and so this is the exam topic, like 35% from routing, 20% from VPN, then 20% from security, and 25% from services. Nothing. So if you click on this L3 technology, you will see everything that you should know from the routing point of view. This is the content, like what is AD value and these things. Something called route map, loop prevention mechanism, route redistribution, summarization, policy-based routing, VRF. There are a lot of terms that you might not have heard of, but there are some terms that you should already be familiar with, such as IPv4, IPv6, like EIGRP is a protocol that we have to cover from both IPv4 and IPv6 routing point of view. OSPF, we have to cover from IPv4 and IPv6 point of view. BGP, we have to cover from both IPv6 and IPv4 point of view. So this is going to take a while, like this entire content just for the layer 3 technology section, it is going to take 15-20 days, 15-20 classes. Then in the VPN technology, we have only this thing. It is 20% of your entire content. Here we are going to focus on like tunnel based VPNs and tunnel less VPNs. Like tunnel based VPN and tunnel less VPNs, we are going to discuss about that. It is going to cover like approximately 20% of the entire content. And see, describe, that means they don't want you to know the practical part of it. They just want you to know from the theoretical point of view, what is MPLS, what is MPLS operations, what is MPLS layer 3 VPN. You should know at least from the theory point of view. If there will be some time, we will do the lab. MPLS is, see, when it comes to transport technologies, like how many ways are there to connect our maybe headquarter with the branches to the data center and all. So we can use two type of technologies, two type of transports. One is public transport, one is private transport. In a public transport WAN services, we have most common example of a public transport WAN service, internet. Internet is most common transport to connect your data center, headquarter, and all those all together. But when it comes to private WAN services, like I want to utilize some infrastructure to connect my headquarter, branches and all, that is not accessible to just anyone. Because if it is accessible to anyone, different types of issues can be there, like attacks can be there. Any attacker can read the data that is passing through. So I want to utilize some sort of private privately owned or private van services. So if you want to utilize any transport that is not public, that is not accessible to everyone, you can go for an MPLS transport. So MPLS is just a transport which provides interconnectivity between branches, data center, headquarters in a little bit secure manner than the internet. Because in security in the terms, accessibility, like internet is accessible to everyone. MPLS is not accessible for everyone. It is accessible to those who have paid for it. So that thing basically. So we'll talk about that in detail, how MPLS operates, why we needed MPLS, what was the requirement of having the MPLS, and all those. We'll talk about that. And then we will configure and verify general tunnel-based VPN. This is going to cover 20% of the entire content, which will most probably be done within like 3-4 classes. Then infrastructure security, we have some security related things such as access list, AAA, we have already configured the user ID passwords on the router. So I want to have a centralized database for all that user ID and password. So for that, authentication, accounting, and authorization. So we want to use that. So we'll do the practical of AAA as well. And then we will talk about some advanced topics in security. For example, like I have a router and that router is having very less resources. That router is having like a very low end CPU, for example, and that router is connected on the WAN side of my company, like on the edge it is connected. Now the problem is someone has started a continuous ping, and that ping is coming onto the router CPU is processing that ping again and again, and it is causing a lot of CPU utilization. So what I want that the router should not even process any such ping messages. Not only ping, but any message that is CPU intensive. So let's say I do not want my router to process the telnet or SSH traffic from outside. Maybe I want to do that. So just in case, if you want to restrict some packet from going to the router CPU or the device CPU, we can enable this feature called COP, Control Plane Policing. This is a feature that restricts the packet going towards the device CPU so that the CPU utilization decreases. So we'll talk about that in detail. What is this? Then in IPv6, we can have different types of security related features. So like in IPv6, first top security concept, we'll talk about security related things in IPv6. So again, 20% of the entire content focused on security, 4 sections only. Again, see one thing, describe. So it is, they don't want you to practically implement it, but they want you to practically implement all the rest of the features. And finally, we have services like, console, VTY, telnet, SSH, FTP, TFTP. Most of the things we have already covered, but we'll revise all those things and then we will see some additional things as well. DHCP, SLA, NetFlow, DNS center. From the automation point of view, this is the only thing that you should know. Nothing else. Like you should not worry about any APIs or programming like Python and all those things. The only thing that you should know, what is this? What is this DNS center assurance feature that is available, and how can you do the connectivity test, monitoring, check the health and all those things from there. They don't want you to create any API call or do anything. Nothing. They just want you to know what is DNS center appliance. How can you use the variety of tools that are there in the DNS center appliance? Between how to and the devices basically, and how we can use that DNS center appliance to query different things from our network, such as device health. How many devices are performing okay? How many devices are performing like not performing okay? The wireless health, wired health, and all those things. So we'll talk about that. So this is like around total. It is 100% of the content that we will see. You can download this, okay, from the website. You can either have it in a PDF format on your mobile. Otherwise, you can have it in a hard copy format. Now, what you had to do, you had to cross check that every topic that is discussed here is done in the class. So you have to actually make sure that nothing is skipped from here. That is, we will do everything, but if anything is skipped, you will let me know that, okay, this topic is not completed in the content. Now, to complete this content, you have some official certification guide. So this is what it looks like. So this is the official certification guide for CCNP ENARSI, Advanced Enterprise Routing and Switching Infrastructure. So like Enterprise Advanced Routing and Services. So this is the official cert guide. You can have it in a hard copy format or the soft copy format. So if you want to have it in a soft copy format, you can have it from me. Okay. And see, there are total 23 chapters that we have to go through. Okay. And chapter number 4, chapter number 10, 8, 14, every chapter that is based on T-shoot, it will be done like throughout the content. Like when we were configuring some topology, I will tell you, like, for example, OSPF neighborship is not coming up. What could be the issues? I will tell you throughout the path. And the same thing what they have done, they have written down in a chapter format. Like, okay, so if the OSPF neighborship is not coming up, these are the possible issues, memorize it. So these chapters will be covered throughout the content, but not separately. This is what you have to do by yourself. On, like, for example, like OSPF, this chapter, once OSPF is done, you can just take a look at this chapter. You can either note down all these things. Otherwise, you can basically refer to the book itself, completely up to you. But you should have, like, you should memorize that if the OSPF, if the OSPF neighborship is not coming up, this is the issue. This is the issue. I don't think, like, apart from the issues that is listed here, I don't think you will face any other issues if the OSPF neighborship is not coming up. So it's good that you memorize all these. And it is for every like protocol. EIGRP, this is EIGRP. So why the EIGRP neighborship is not coming up? These are the possible issues. Memorize it. I don't think like there will be any issue other than this one when you are doing the T-shoot. And if we get some time, I will give you one T-shoot lab as well. So do it by yourself. Earlier we used to have a website, and from there you can practice the T-shoot, but that website was based on Flash player, and that Flash player support ended actually, so that website is of no use nowadays. But I have downloaded all these files that are there, so I can give you those files. Those files are in packet tracer format. You can just download those files and you can T-shoot. There are total 16 tickets that you can T-shoot based on the knowledge that you get. 16 issues, 16 problems are there. There are 16 different packet tracer files. In every packet tracer file, there is one issue. You have to identify what is the issue and you have to give the resolution based on the knowledge that you got from the chapter. So I have we'll talk about that throughout the content, like EIGRP, OSPF. One topology we will cover, and one topology I will give you to cover by yourself. So like GNS file I will give you. So one topology we will be covering in the class. You have to practice that as well. But after that, once that is done, once you have practiced that one, then I will give you one topology to do it by yourself. All the documents and everything, what you have to do, what commands you have to run, everything is there in a documented format. I will give you that. You have to just practice from there. Okay, so this is the official cert guide that we will be, see what I will do. Let's say, for example, we went through our slides and our chapter 1 was done. So what I will do then, after we are done with our slides, let's say for the first chapter, I will open this book, I will expand this, and we will talk about everything that we have done. We will go through everything, not verbally, but everything that, okay, this topic is done, this topic is done, this topic is done. So that means like once this chapter is done, it is done. Like there will nothing be left from that chapter. Now it will be your responsibility that in your Friday, Saturday, Sunday, you revise all those chapters, you practice, and just in case if you have any doubt, you let me know. Okay, so this is the official cert guide. And
So I have
yeah, this one is. Mhm, mhm, mhm,
like most of the important stuff
mhm,
about switch,
mhm.
NAT, SCP. This is like very interesting.
Yeah, then it will be very good.
And you will like understand.
Mm. If you have all, see what happens, like in most of the cases, generally students, they do not go through the book because they find it a little bit hard to understand the language that is there in the book. It is a little bit hard to understand. It is a little bit boring. It is not that much interactive, that much interesting. But when you go to the professional or even expert level of certification, you will not find any third party book. You will find official Cisco certification guides. And if you're not habitual to studying these books, obviously you will not be able to understand the things in detail. So it's a very good thing that if you have covered like at least from the books, if you have covered the things, you will find this book as well, like same interesting. Mm. Mhm.
Facing that issues like
Mm.
times because frankly I never like booked before. I don't have that habit of reading books.
No issue. So mm,
Step by step. But when I like I'm reading these books like I found it like very
it is in very much detail as well. And let me tell you, see, for example, see here, just an example. Here they have talked about LSA, okay, which is just one of the component of the OSPF. Now, in this book, they have talked about all the LSAs that are required for our network in detail. Pretty much in detail, they have talked about this. When you go for the core exam, they have not described all those things. So it is a must that you have to go through this book, because later on when you go for the core exam or the core curriculum, core content, it we will assume that you know these things. We have to more like give you the overview rather than cover everything from the scratch. So that is why I would recommend you to like go through the book, throughout the content. As soon as we complete one chapter, go through the chapter. You will have plenty of time. You will have like 3 days, 4 days, 3 days at least in a week, like Friday, Saturday, Sunday. You will have complete day. Then even normally you will have like plenty of time, so you can easily go through this. Now, like the labs, about the lab. So this is the lab that we are going to do. I will share with you all the documents with the help of the portal that we have, Trainonic. So I will share whatever documents are required. So this is the lab that we are going to do. So we will be doing these much labs. So we have approximately one basic topology, then we have OSPF, then we have, in the basic topology, we'll talk about just basics, routing, what is routing and everything. Then we have like OSPF, DMVPN, VRF. Base topology is we will be using this for like static routing and EIGRP. So then BGP, then DMVPN and IPv6. So we have some topologies. This is what we will do in the class. This one. So once we are done with this, let's say for example, I'm done with OSPF. Now I will give you this. This right here. This has 4 labs. This has, if I open this has in total, let me show you. So this has 4 documents, means 4 tasks that we have to do. And this is the topology. Obviously, we will not be doing this topology, but this is the topology. Okay, just a minute. Yeah. So this is the topology. So this topology is already there. Configurations are already there. You just have to read the document and you have to provide the solution. And nothing from this document will be out of our content. Everything from this document will be within our content. And same thing we will go for BGP. Same thing will go for EIGRP. Same thing will go for other things, like this is the T-shoot that I was talking about. So this T-shoot, for example, has like this topology. There are total 16 tickets, and you will open one of like each of them one by one. In every ticket there is a problem that you have to solve. First of all, you have to find whether no. It is the final topology. You will never know in the ticket what is the issue, because that is like giving you the half solution. If I tell you that this is the IGRP issue, so that is not there. So every ticket, it can have anything random in random. Any problem from your entire CCNP, in this one there will be in random. So that and very small issue. There are chances that you might not even think about that issue. Very small. Maybe the interface will be shut down and you will troubleshoot OSPF IGRP, but you will not. Yes, that exactly that thing. I said, like, you have to know that if the OSPF membership is not forming up, why it is not forming up. First of the criteria there is the interface is shut down to all the way up to the layer 3, layer 4. So you have to follow you can follow any approach you take. Either you can follow 1 to 7, you can follow 7 to 1. I generally do not go like that. I start from L3. I do ping if it is successful, or if it is dropping at some point, I will do trace. Like I do ping. I see that the ping is getting dropped. I do the trace. I see like trace is dropping where. If the trace is dropping from like at the first hop, like that means the problem is there between your PC and the first hop, not beyond that. Why should I troubleshoot beyond that then? Maybe my gateway is incorrect. Maybe the VLAN is incorrect because my packet is not even going to the gateway. Otherwise, I should have seen that in the trace. So everyone has their own approach. So both are okay. In T-shoot, we used to teach that top-down approach, bottom-up approach, shoot from the hip, divide and conquer. There were different approaches. But thing about T-shoot is that it will come from practice. It is completely up to you. Like there is no fixed way of T-shoot. Every way is the right way for T-shoot. It is just how quickly you get the answer. Sometimes, like let's say I just did a ping, I did the trace, okay, and but just by looking at the trace, I came to know that packet is not even going to the gateway. I checked my gateway IP was incorrect. How long will it take? It will take approximately 2-3 minutes maximum. It will not take more than 2 minutes for me to ping and trace and everything. If you go from 7 to 1, it will take time. If you go from 1 to 7, it will take time. Exactly. So T-shoot, you will study throughout the content in our case as well. Maybe our BGP neighborship will not come up. We will troubleshoot why the neighborship is not coming up. So you have to memorize why the BGP neighborship. So this was the issue when the BGP neighborship was not coming up. It might be the case. So we'll go through that throughout the content. Okay. Now, so this is about the labs. Most of the labs we will be doing on the GNS software. Otherwise, you can use EU as well. And yeah, even EU is one, yeah, EVE next generation. So EU is one of the platform that most of the network engineers use nowadays for topology creation and everything. It is a very well, very well made platform. It supports not only Cisco but other vendors as well. See, we will use both actually. In GNS3, we can practice most of the things, like 80-90% we can practice everything. But for example, we cannot practice switching here. So where will you practice switching? You will practice switching either on the real devices or on the Eve, because we have switches for Eve as well. Like we have the images for switches in Eve as well. Yes, there is actually, you have to integrate the GNS3 VM. So if you integrate the GNS3 VM, you can use the same images that you have in the Eve and you can deploy it here. But honestly speaking, using a GNS3 VM versus using Eve, Eve is much more convenient. Like it is more easy to understand the user interface and everything of Eve than GNS3. Whenever we go for the switching section, I will, perform every lab on the real devices. And anytime if I have to use any software, I will use Eve. So there are a few limitations in Eve as well. Like for example, if you say show history, nothing will show up. So there are few limitations, but you will find Eve more accurate than GNSM. So, and it supports like latest images as well. Eve. Here we will be working on iOS version 12.4 or 15.0. Some things that mostly we'll be talking about iOS 12.4, and 15.0 is the version that is supported on the GNS if you want to practice on iOS 15. And current version of the iOS, it varies from router to router, but 15.9 is one of the latest version. So practicing on 12.4 versus practicing on 15.9. So that is why I would recommend you that if you have the laptop and resources, I would recommend you to set up EUNG onto your machine. Sorry? Yeah, I would recommend that if you have a laptop, you set up EUNG onto your machine and practice things on Eve more than on GNS. Now, see, we will be doing everything on GNS as well. We will do everything on GNS. Hmm. Huh. We'll see. We'll see. We'll see. No issues. See, we will be doing everything on the GNS as well. Normal GNS without VM. So it will not require a lot of resources or anything. But later on, some things like, for example, switching, if you want to practice at your home a little bit, you can utilize this platform as well. Completely up to you. Fine. So books and everything I will share with you on the portal itself. So you can find it on the same Training portal, and documents and everything. You can either download it from here. Otherwise, you will find this on the portal as well. And the labs and everything you will find on the portal as well. Okay, so everything I will share with you, and PPTs and everything. See, hard copy you already have. Okay, but from the quick review point of view, I think like you might find it on the same portal as well. Otherwise, you can just refer to the PPTs, that hard copy format that you have. Yeah, now I'm coming to that. This is the time that we will take for NRC here. Approximately 40 days it will require. 40 classes actually. Yeah. So I believe it is 3 to 5, 3 to 5, no? The timing. From 40, this is 40 days, 2 hours a day. So around 80 hours classes you will require. 80 hours. So like 40 days, 2 hours a day. So if you divide like 80 divided by 3, so that will be like around how much? Around 25, 30, approximately 25, 26 days, 27, 26 days classes. Yeah, approximately. Because 3 hours a day is going to be, we'll be able to cover that much. So we will need at least like 4 days from the 2 hours a day point of view. Like 4 days for basics, like what is routing. We'll revise the OSI model, network layer and everything one more time. So we'll talk about OSI 4 days. Then we'll talk about IPv6 routing, at least for 3 days. Then we will talk about static routing for 3 days. Then we'll talk about the IGRP for 6 days. Not 6 actually, 1, 2, 3, 4, 5, 6, 7 days. 7 classes for EIGRP. And then for OSPF, similar, approximately 7 classes for OSPF. Then BGP, approximately 9 classes for BGP. BGP is quite, different than the IGPs, so it will take a little bit more than the IGP. So 9 classes for that. And yeah, so yeah, so and the types of neighborship and everything. So approximately 9 days systems. Yeah, so 9 days for BGP and 1, 2, 3, 4, 5, 6, and 7 days for rest of the content like VPNs and everything. So day wise, if you talk about like it is going to take 40 days, 2 hours a day, 40 classes, 2 hours a day. And if you convert it into 3 hours a day, it will be approximately like 26, 27 classes. So which is going to go approximately 1 month, most probably. 1 month, 1.5 months for routing, 3 hours a day. And if you go for switching, this is switching. It takes approximately 24 days, 24 classes. By days, I mean classes. 24 classes for switching. So 24 classes means 48 hours. And if you divide it by 3, it will be like 16 days, 16 classes. So consider 3 months for routing and switching complete, approximately. So I will share like this thing with you as well. If you want, I can share this thing so that you can have a track what things are going on. But this is bare minimum what we have to cover from our content point of view. We will not skip anything. We'll try to not skip anything from the content. This is how long it is going to take anyway. So it is comparatively, like if you compare it with CCNA, almost similar amount of time that you took in CCNA, it will take in here. It will be almost more than that, I believe, because route and switch, both the things, if you combine T-shoot and everything, it will take. So, and if you have some time period, we'll talk about some big topologies as well. Like if we get some time, we'll talk about some production level designs, and we'll talk about what protocol has been implemented, switching, routing, and everything. So we'll see according to that. So this is what we will be covering. So
Primarily, like this training, I want you to attend like ASFI was training.
okay. You should know before we start this content, you should know basics of routing. You should know, like, for example, what is IP, what is IPv4, IPv6, what is routing protocol, what is routed protocol. Those things you should at least know before this fundamental. Otherwise, what you can do, like, for example, let's say I have to start OSPF tomorrow. So what you can do, you can just quickly revise the OSPF from the CCNA so that you can have more discussion in the class. Okay, so that will be better. We will discuss the things from the CCNA little much, but not that much. Like, for example, I'm not going to talk about IPv4 classes, class A, class B, class C. I'm not going to talk about subnetting and everything. That I will think that you already know. Even if you have any question from the CCNA content, you let me know. We can have a separate discussion. Okay, but from the content point of view, we will stick to the content strictly. Like whatever is there in content, we will discuss that first. We'll prioritize that. And apart from that, small things that we have to discuss, we'll discuss that after that. Anytime you have any question, you let me know. Okay, we can have a discussion, or you can, for example, like when we are discussing something and you get some question, you can note it down. After the class, we can discuss the question, whatever suits you. Okay, completely up to you. Everything will be recorded, so you can actually refer to the recordings later on. And if you have any question, you can discuss in the starting 10 to 15 minutes of our class from the previous day. And then we can begin our new content. Next day again, you refer to the recordings, read the books, theory and everything. And if you have any question, again, next day, the starting 10, 15 minutes, we can discuss, and then we can start the next class. All right, so first thing that we have to start is the routing protocol fundamentals. This is basically chapter 1 from your NRC content. So to study this, you have to go through the chapter number 1 from your official certification guide. So we have to talk about like what is IP routing process, how routing happens in the network, and what steps are involved when it comes to routing in the infrastructure. So to understand that, first of all, like what is IP routing process, like what is routing? So forwarding of the packets based on the layer 3 address is what we call as routing. And any device that can forward the packet based on layer 3 address, which is, you know, IP address, is what we call as layer 3 device. So if someone asks like why the router is a layer 3 device, you will just say because router makes its forwarding decision based on layer 3 address, which is an IP address. That makes router a layer 3 device. So forwarding of the packets based on layer 3 address, which means IP address, is what we call as IP routing or layer 3 forwarding. Devices that can switch the packet based on the layer 3 address, they are known as layer 3 devices. Commonly utilized layer 3 devices are router and a layer 3 switch. See, when you are doing switching section, you must have come across the concept called inter-VLAN routing. In the inter-VLAN routing, you should have seen that there are two approaches to perform inter-VLAN routing, one by using a router and one by using a SPI, you know, switch virtual interface. So remember from that class that on the switches, we can also enable the routing so that the switch can route the packet from one network to the other network. That is the router on a stick where we use a router, and using SPI where we use a layer 3 switch. Yeah, so layer 3 switches are also capable of doing the routing in the infrastructure. Firewalls can also do the same. So firewall is also one of the device that can do the same. Okay, now layer 3 devices, like let's say this is a router. Let's say this is a router. How this router is going to decide that if I have received a packet, out of which interface the packet has to go. So see, the only thing router cares about is the exit interface. You tell the router, oh, you have received the packet on this interface, do one thing, place the packet onto this interface, and the router will do that. The only thing that the router is worried about is how to, or on which interface I have to place the packet. And that will be done based on what? Routing table. So layer 3 now layer 3 devices maintain a table called routing table. And in the routing table, what is there? In the routing table, routers or layer 3 devices maintain destination network information. Like for example, you have to go somewhere, so you have memorized that, okay, if I have to go there, I have to take this path. So you have maintained in your memory that if you have to go to a certain shop or certain destination, this is the path that we have to take. Routers can do the same. Routers can memorize. Router can store the route information in a table called routing table. So layer 3 devices maintain a routing table, and in that routing table, they maintain what? Destination network information. Remember the difference between the switch and router. Switches, they learn what? Source MAC address, and the routers, they do not learn anything. They just receive the packet, they check the destination IP address, and based on the destination IP, they make their forwarding decision. They do not learn source IP from there. Routers, they perform destination based routing. That means routers or any layer 3 device, it is going to take a look at the destination IP, and based on the destination IP, it will decide where to forward the packet. There is also something called source based routing. In the source based routing, the device has to consider the source IP as well. But routers and these devices, they do not do that. We will do the source based routing as well in our content later on. We'll talk about what is this source based routing, in which condition the router will also check the source IP of the packet before making the forwarding decision. But at the moment, we are just going to talk about destination based routing. So packet is received on the router interface 0 by 1. A router will decapsulate the packet, and after decapsulating, the router will come to know what? The destination IP, and it will check that destination IP where? In the routing table. And from the routing table, it can decide where it has to place the packet. And see, they check the routing table just to know the exit interface, like out of which interface I have to actually place the packet. So if I have to go to a certain destination, to go to that destination, what is my exit interface? They get that information. They look up what? The routing table. Okay. In the you must have seen the routing table quite a lot of time. This is how the routing table looks like. And in the routing table, what content is there? So if you use that show IP route command, first thing is what code, which just represents like the way the route has been learned. Yeah. So what is this? If you see something like this, gateway of last resort is this to the network this. This is an indication that you have a default route in your network. So if you have a default route on your router, you don't have to scroll through the entire routing table. You just have to take a look at there. This is the next hop. I hope you are familiar with the next hop. And this is the network. What is this 0000? 00 means any network. IP starts from, see, every IP address has like two components, network part and the host part. Every IP address has like network part and it has the host part. Remember, if the host part is completely 0, it is what we call as network address. And if the host part is completely 1, it is what we call as broadcast address. And if I say, let's say I have written down an IP address 10.1.1.99/24. What does this mean? First of all, is it an IP address or is it a network ID or is it a broadcast ID? So just by looking at this, I know 24 bits are for what? Network, and remaining 8 bits are for what? Host. So these are 24 bits. They are for network, and this is what? Host part. Do you see this host part as complete 0? No, that means this is not a network ID. Do you see this host part as complete 1? No, that means it is also not a broadcast IP. This is just an IP address, which is host assignable. We can assign this address onto the host machine. Now, which range this IP address belongs to? So if we had to find out like this IP belongs to which network? No. This, no, yeah, 10, but what? This IP address belongs to which network? It like 10.1.1.0, na? Yeah, that is correct. So how you come to know that this IP belongs to this network? You have based on the subnet mask. So 24 bits were for network, remaining bits were host. Host bits could be anything. So if I had to write down the network ID, I will just write down this. Like you think about it, first IP of every range will always be what? A network ID. And last IP of every range will always be a broadcast ID. Think about it. First IP of every is going to be the network ID, and the last IP of every range is always going to be the broadcast ID. The rest are going to be host assignable.
Okay.
Let me know if you have any question.
It's like broadcast, it's not like assignable.
Same thing. This is not host assignable. This is not host assignable. In between the range, we have host assignable. Okay. So you said like this is based on this. You said 10.1.1.0 is what? Network ID. Okay. What is going to be the broadcast ID then? 10.1.255. Okay. So you say this IP belongs to this range. Okay. That is correct. Okay. First IP is network ID, last IP is broadcast ID. You say this IP belongs to a range that starts from here and ends from here. That is why the first IP you are calling it what? Network ID, and the last IP is this IP represents what? This IP represents the entire network. Entire which network? 10.1.1's network. This IP represents the entire 10.1.1 network, 10.1.1.1, 2, 3, up to what? 254, 255. Now, what about you have to write down a network ID and broadcast ID for entire IP range 0 to 255. Then what it will be? Entire IP range, like class A to class. Okay, and what will be the broadcast ID? Yeah. Okay. So what this is going to represent? Which network? Entire network. Exactly. So this is what? Exactly. So it means it means that if you have to go to anywhere apart from here, where you have to go? Here. That is why we call this what? Default route. We call this default route because it is a default path to reach to anywhere apart from what is available in your routing table. So this 0000 is also what we call as gateway of last resort. This default route is what we call as gateway of last resort. That means if you do not have a route to reach to exact destination, follow the default route, send the packet to the next hop, the packet will get delivered somewhere.
Yes. Don't have the exact network.
Right. In the routing table, na?
Yes.
That happens.
Just establish network, right?
Yes, from the CCNA point of view, yes.
Yes.
Huh.
Right. This is like it's not like just for stub network. We can like
We can have it on normal cases as well. It is no problem. We prefer it to do it on the stub networks. But see, if you do the default routing in a not so stub network, you do the default routing in like random any place in your network, it might cause routing loop. That is why we prefer it on the stub routers, but it's not mandatory that we cannot do it on we can do it anywhere. We can do the default routing anywhere, but we prefer it. Yeah, we will prefer it on the stub router. Let me give you one example. Let's say we have two routers. This is what? Internet. And we have a default route, we have a default route. Now think about it. If I have, this is my internal infrastructure. This is internal infrastructure. And we have like 4 or 5 routers inside. And we have some switches and all. Let's say I have given a default route here. And here also I have given a default route somewhere. So now what will happen? If a router receives a default route from here, and if a router receives a default route from here, which one it is going to accept? Let's say it accepts this one, then it's okay. Then you can reach to the internet. But what if it accepts this one? Then what? It might loop around, the packet might loop around in your internal infrastructure itself. So it's not a good idea to perform routing. Default routing is specifically there on the just random routers. It is always preferable on the stub routers. But it's not a hard and fast rule that you have to do it always on the stub routers. It's not like that. From the CCNA point of view, that is okay.
it is just like we don't like to this default route from the stub route.
On this,
Some cases.
yeah,
But we have to identify.
Yeah.
Like,
you have to carefully analyze the network, and you have to see where should we use that default route statement, so that it might not cause any routing loops or anything. So anytime if you see this, immediately think about default route. So if you have to go anywhere, you have to go to this next hop. Now one more thing I would like to tell you, it's not always this. There might be some conditions where you see something other than this being a default route as well. Do not think default route 000. I can mark if I want. In my network, I can mark maybe this as a default network. By the commands, I can mark that 000 is not 10.0.0.0 1/8 will be my default route. I can mark that. So it is like in most of the cases, 80-90% cases, you will always see this. But there are conditions where we can just randomly mark any network as a default route. Do not think default route means 0000. That's what I'm saying. Default route is just a path to reach to the destinations which are not available in your routing table. It could be anything. Do not get confused by this 0000. It could be anything. Fine. So C stands for connected. L means local. That means what you have configured onto that interface. So whatever IP you have configured on that interface, it is shown you as a route here as well. D, dual EIGRP. D means EIGRP. EX means external. S means static. O means OSPF. So these are the codes by which you can identify that from which routing information source you have learned the route. Now this is what AD value. This is what metric value. Yeah, in OSPF we call it cost. In EIGRP we call it composite metric. We'll talk about that in EIGRP section. Remember, static route, they do not have any metric. So for the static route, metric will always be 0. Always. You cannot define any metric for static routes. Now, so in the routing table, you have network ID, subnet mask. What this represents? This represents that if you have to go to this range, exit out of this interface. If you have to go to this range, exit out of this interface. If you have to go to this range, exit out of this interface. So we have a range of IP addresses that are reachable from that device point of view. And range is not represented like from to, it is represented in network ID / subnet mask format. Network ID and CIDR format in the routing table will represent the range that the device knows. Code means how you have learned that, ADN metric, next hop IP address, exit interface, all that. Fine. Now, why do we have these things such as, one more thing that you should notice from this routing table is that you do not have the route to reach to exact IP. You have the route to reach to a network, which includes that IP. Because think about it, if I have a router and I have a switch here connected, and let's say I have connected here, let's say 10 users or 20 users. I have connected 10, 20 users here. If the router starts maintaining the IP address of every PC, it is going to consume a lot of resources of the router. This routing table that it has created is also going to consume some resources. So it's not like router is having infinite number of memory, or router has a limited amount of resources. And if you are going to maintain like, if you are going to keep a lot of information in the routing table, it will obviously consume a lot of resources. So routers, they do not maintain in the routing table. They do not maintain the route to reach to every IP. They do not store the exact IP information as a route in the routing table. They just store what? Subnet.
To do the route, just
if that is a condition, then it is okay. For example, like if you have a finance department, in that finance department you only have one user, and you have allocated a /30 subnet mask to that department, and you want to give a specific route to reach to that IP only, so that even if that user changes the IP, it becomes unreachable. So in that case, it is okay. But in most of the cases, you will see that is administrator given. That is not maintained by the router automatically. So routers, maintain this routing table on per subnet basis. We call this prefix. This we call prefix. So anytime you hear the word prefix, just think about subnet or think about network. And anytime you hear prefix, what? Length, think about what? CIDR. Subnet mask. This. So this is prefix and prefix length. And we combine them, and what we get? We get a route. So what is a routing table? Routing table is a collection of best routes to reach to all these destinations. Now, what is this AD value? AD value is in like definition terms. AD value is what? Trustworthiness of what? Routing information source. So from where you are receiving that route information and how trustworthy is that information, that is what is defined by what? AD value. AD stands for administrative distance. Now think about it. AD is just a number that ranges from where? 0 to 255. 0 means what? Most reliable, and 255 means what? Least reliable or untrusted or unknown. Any route that is not installed in the routing table has an AD value of 255. You can say that. However, that is not true. Some people say that any route that is not there in the routing table, that means router does not know about it. And if the router does not know about it, that means the AD can be considered as 255. But have I configured that? No. How can I say, if my router is not even having a route to reach to a destination, how can I say what is AD? What AD is going to be there for that particular route? So it's not exactly the same thing, but some people say that. Anyway, 0 is reserved for what? Directly connected. Only directly connected. So if, yeah, 0 is for what? Directly connected. So if I have, static has 1. So if I have networks that are directly connected to the router, that will have AD value of what? 0. Okay. Now 0 means what? Most trustworthy. That means a route with the AD value of 0 is always going to be preferred over anything else. That means router will always prefer its directly connected subnets than anything else. So if TENS network is directly connected to the router and the router is also receiving the same subnet information via EIGRP or via OSPF, OSPF has an AD value of 110, it will always prefer what? The one which is directly connected. In between, the AD values are, some are predefined, and we can customize it as per our requirement. We can change the AD value for static route. We can change the AD value for routing protocols as well. The question is, why there is an AD value? Why the router uses AD value in like actual terms? No. AD value, based on the AD value, the router decides which route will get to install in the routing table. Because router has to maintain the routing table. I might be getting same information from 2 routing information sources, RIP and OSPF. So which one is more trustworthy? So the one with the lower AD value is what? More trustworthy. So that will get to installed in what? The routing table. Now, before this happens, before the router decides that based on the AD value, I have to keep, or I have to put OSPF path in the routing table. Before that, there is also one condition. Let's say from one of the routing information source, you are getting this route. Okay. And from the other routing information source, you are getting this route. Then which one will get to install in the routing table?
Who has the less?
Okay.
Less 30 will prefer.
Uh,
Because they are the same subject.
they are not same subnet. That is the tricky question. They are not the same subnet. It looks like they are the same subnet. There is a difference in the subnet mask. There is a yeah. So remember this thing like if the router will install the route with the via RIP routing protocol or via OSPF. These things come after this thing. If the router is receiving a route from two different routing information sources, but their subnet mask is different, the router cannot actually compare these based on what the AD value. The router will install both. Why? Because this represents a different range of IP addresses that are reachable, and this represents a different range of the IP addresses that are reachable. You don't get that? No? Think about it. If you do the subnetting, what will be the range? It will be 10.1.1.0 to 10.1.1.3. If you go here, if you do the subnetting, the range will be 10.1.1.0 to 10.1.1.15. Okay. Now, if the router installs this route in the routing table, the router will only have the route to reach to 4 IP addresses, 0, 1, 2, 3. And if the router installs this in the routing table, the router will have the route to reach to 15, total 16 IP addresses. So if you think about that from that point of view, since this represents a different range and this represents a different range, the router cannot actually choose this is coming via RIP AD value of 120, this is coming via OSPF, or this might be coming via OSPF or RIP, or this might be coming via OSPF. Does not matter. Yeah, they are not the same routing protocol. See, I'm connected from router 1. I'm connected with router 2, let's say via multiple cables, or maybe I'm connected like that. Router 1, router 2, and router 3. And here we have that tense network. Okay. Now this router is advertising that tense network via OSPF, and this router we have run RIP routing protocol there. So the router 3 is advertising via RIP. This is advertising this network on /28, and this is advertising it on /30. It has to choose one of them. It will not choose one of them because their CIDR is different. Remember what we are talking about. We are talking about installing the route in the routing table. We are not talking about data forwarding. We are not talking about out of these two routes, which route will be taken by the router to go to the destination. We are just talking about out of these two routes, which route gets to install in the routing table. And that will not happen if they both have different CIDRs.
If we both have the same CIDR,
Then that thing AD will come. Then AD will check. So if both were coming on /28, then the router will choose the one with the lowest AD. Yeah, so in that case, OSPF will become winner because it has the AD value 110.
but if we have two different the same routing protocol, they should like based on cost, right?
If it has same, if even if that is like same CIDR, same protocol, then it will go to the third criteria, which is metric. Yeah, so after AD, it will check what? Metric. In case of OSPF, what is this? Cost. So now it will check like if I go via this path, what is the cost? And if I go via this path, what is the cost? and based on that, it will decide which one is the best one. Lowest cost is always the best.
In the concept of small the length of prefix, we choose the longest prefix.
That is for data forwarding. That what we are talking about, the longest prefix match. Yeah, that is for data forwarding. But when we talk about installing the route in the routing table, that criteria is not applicable because two different CIDRs represent two different ranges. And for two different ranges, we cannot make the decision. We cannot make the decision based on whichever has the lowest AD or lowest metric. That cannot happen. And even if the metric is same, let's say if I follow this path or this path in both the cases, even if the metric is same, so the last thing is what? Load balancing. That is okay. And the type of load balancing that will be done by the device is what we call equal cost multi-path, ECMP. Equal cost multi-path means equal cost load balancing. That means if I have 10 packet, I will send 5 packet from the one path and 5 packet from the other path. EIGRP is the only protocol that can support unequal cost multipath as well. Yeah, that means EIGRP can distribute the load unequally, like out of 10 packets, 7 packets from the first path and 3 packets from the other path. We'll talk about that in the EIGRP section. Okay. Now, here itself, few more things that you should know. See, this is a Cisco router. This Cisco router supports different routing protocols, such as it supports what? Static routing. It supports what? RIP. It supports EIGRP. It supports ISIS. It supports OSPF. It supports BGP and others. Cisco router supports all of these routing protocols. So what do we mean by Cisco supports all these routing protocols? Is that the Cisco operating system, which is what we call as iOS, is implemented. It is all these protocols are implemented into that iOS, and accordingly we can run any that we want. Now, on the Cisco devices, that is okay. But what about the non-Cisco devices? In the non-Cisco devices, we might not see protocols such as EIGRP. So it is a proprietary protocol. In 2013, they made it as an open standard, but no one has implemented it. So it is still like it is open standard, but no one has implemented it. Now my point is, if let's say I am Cisco, let's say I am specifically talking about this Cisco vendor. When Cisco people, when the Cisco team, Cisco manager or whatever you say, CEO, whatever you say, when they created their own operating system, which protocol gets preference over the other protocol? Who will decide that? You say it is done based on the AD. Who decides this AD? You know that OSPF AD is 110. Who said that? Like we are going to use. Yeah, who implements, not who has created. I created OSPF. I gave you the OSPF as an open standard protocol. Now you implemented it onto your operating system, iOS. You choose your preference. Obviously, if I made EIGRP, I will prefer EIGRP over any other thing, na? Because that is my protocol, that is my proprietary protocol. So think about it. This number that you have memorized, it is only for Cisco devices. In my operating system, what is the AD value of RIP? It has nothing to do with what is the AD value of RIP in HP router or Juniper router or any other router.
That's why it is configured.
Yeah. Why we use AD? We use AD so that if the router gets to know about a route, via different routing information sources, there has to be some preference based on which the router chooses the best. But what is that preference? I will decide because I am vendor Cisco. So this number, first of all, is locally significant on the device. AD value is never exchanged between the routers. What AD I have configured on one router will never go to the other router. You have already done the static routing. You must have done the static floating routing, where you change the AD value of a static route. Think about it. You change this AD value of a static route on one router. You have to change it on the other router as well. It will not change automatically. Yeah, you have to change it on the other routers as well. Yeah. So if you are running OSPF and you change the AD value for OSPF on router 1, it will not automatically change it on router 2. You have to change it on router 2 as well. So AD, first of all, is locally significant value. It tells the local router which protocol you have to prefer over other protocol. It has no significance on other routers. In my infrastructure, I can have 10 routers, and on 5 of the routers, I can have AD value for OSPF as 100, and on 5 routers, I can have AD of OSPF as 200. What difference would it make? I can have different AD values. Whatever AD values there, they are not going to be exchanged to each other anyway. I can have whatever AD value I want. Just remember, if on these 5 router, I receive a route with a better information, better AD value, that will be preferred. If I receive the route with EIGRP, AD value is what, 90 there. So that will be preferred in that case. Na? But you cannot say that AD value is exchanged between the router. It does not happen.
Who has like AD value 100 and other router has
200.
200. 100 is preferred.
No. Think about it. The point I'm trying to make is that this router, AD value will be used by this router when this router has to decide which of these two paths is the best one. This router will use the AD value locally to decide which one is the best one out of these two. But what AD value I have for OSPF, it has no connection with what value of AD is there for OSPF on the other router. It is just local. I do not care what AD value is there for OSPF on the other router, but I know that I will have the AD value what? 100 or 110, whatever. So see, I told you that the only thing router needs is the route in your routing table. It does not matter from where that route came from. See, let me give you one example. Okay, let's say, think about it. Let's say I have configured, here we have one network, let's call that A. Here we have one network, let's call that B. Okay, I have configured RIP and I have configured OSPF. I have configured RIP. I have configured OSPF. Technically, we can run multiple routing protocols on the router. So this route will be carried by RIP routing protocol as well as what? OSPF routing protocol. This route will be carried by RIP routing protocol as well as the OSPF routing protocol. That means now this router has to choose if it has to go to B, which information is better, RIP or OSPF. Now this router will choose based on AD value that OSPF is better. So this will install the route in the routing table via, and it will put the code what? O. O means what? OSPF. Now let's say on router 2, I have changed the AD value of OSPF to 150. Then what? This router will now check that if I'm receiving the route via RIP, AD value is what? 120. And if I'm receiving it via OSPF, the AD value is what? 150. Which one it will choose? 120. RIP one, na? So in the routing table, the route will get installed via what? RIP. What difference does this make? You have the route in your routing table now in both the cases. Do not think like this, that if I have OSPF here, I should have OSPF here. It's not like that. AD value just defines like the router is going to prefer which routing protocol over which routing protocol. That's it.
This case.
Uh-huh. No matter what vendor is there, I can change the vendor. I can configure the AD value as per my requirement. It does not matter.
Like configuring, changing the AD value.
I wanted to prefer RIP over OSPF. I trust RIP more than OSPF. On my router, on my implementation of the router, on my implementation of the operating system, I prefer RIP over the OSPF. It does not make any sense actually. It does not matter from which routing information, which routing protocol you have received the route. You should have a route in your routing table. Till you have the route in the routing table, packet will be forwarded. Routers, they never check that, oh, if I have to forward this packet, I must have received the route via OSPF. They do not check that. They just check the destination. It does not matter from where you have received that route.
How to protocol made just for made it.
They made it. They are made just to exchange the information of the routes automatically. Create the routing table. Now it does not matter. It does not matter that the router chooses which one over which one. Till I have a route in my routing table, it's okay.
So, for example, production environment, my organization prefer RIP.
Huh.
So I would configure RIP, have the lowest, for example,
AD value.
like,
Yeah. So that I can exchange the route. I can install that route via RIP in my own routing table as well. Completely possible. But think about it. Let me show you one thing. You see this. You see this. This is a chart that represents the AD value of different routing protocols on different vendors. Now see, on Cisco, we have directly granted AD value of 0, which is same everywhere. What is this? And you see, EIGRP is not even supported on anywhere else. What is this? In OSPF, we have 110. Here we have what? That means they prefer 1060. They prefer OSPF over static routing. What is this? IS. What is this? BGP. So it does not matter. The point I'm trying to make is that it doesn't. They don't even call that AD. They call that route preference or preference. They don't even call that AD. They use a different term for the same. Yeah, every router will use the AD value routing table. Yes, to update the entries, update the routes in the routing table. It in its routing table, it will choose like which protocol gets to install the route in the routing table. If I'm receiving to go to a destination, if I'm receiving that I can reach to destination A via 3 path, which path is the best? That will be chosen based on AD value. Condition CIDR must be same for all these, because if the CIDR is different, no election, all of them will get installed. If it is 24, if it is 25, if it is 26, since those three are three different ranges, the router will install all of them. But if the CIDR is same, AD will come into the picture. And if AD is same, then it will go to the metric. And if the metric is same, then it will do the load balance. Huh. Rep. Okay. Huh. They will not. They will not. They will not. Here you have to configure RIP. Here you have to configure OSPF so that OSPF and RIP messages are exchanged. I am receiving the same route via RIP and via OSPF, and I am choosing RIP over OSPF. That is my preference.
And there is in the
On router 2, I can have OSPF being preferred over what? RIP. I'm not saying that you have to configure only one protocol here. You have to configure OSPF on both the ends. You have to configure RIP on both the ends. OSPF will exchange its messages. RIP will exchange its own messages. Both will carry the route. But which one I will prefer on my router to install the route in the routing table? Yeah, everyone has its own implementation. My Juniper devices or other vendors, they might prefer maybe OSPF over static routing. Who knows? So when we work on different vendors, you have to be aware of the fact that that vendor has implemented like which routing protocol over which routing protocol. Since we talk about Cisco everywhere. Even if someone asks what is the AD value of RIP, you just say 120. You don't even think about the other vendors. That is the Cisco market, because you don't even think about the other vendors actually. No one does. No one does. Not only you, no one does actually. If they ask you what is the AD value of OSPF, you will immediately say 110. However, you just saw that the AD value for like OSPF is different on the other vendors. So yeah, you have to see that it is based on like the protocol which is widely the product which is widely deployed, which has like even in the interviews and everywhere, they ask the question based on the same.
concept in office concept is how to change like how to create your own router table on different vendors.
Yeah. You should know that if the router has chosen EIGRP over OSPF, on what criteria it has done that. Any questions up to this point? Let me know. Anything? Okay, then I have one question, which I will not answer till the end. So you have to find it by yourself. Now the question is, you will find it very easily if you look on the internet. Same thing. I have A here, I have B here. This time, even the same vendor. It is Cisco. I have implemented RIP, OSPF, and EIGRP. I have implemented RIP, OSPF, and EIGRP. That means these can exchange the messages routes via RIP, via OSPF, and via EIGRP. I can choose to prefer OSPF over any other onto this router, and I can choose to prefer EIGRP over any other onto this router. That I can have. What if I set the same AD value for all these three? What if I set the AD value same for all these three? I went under the router RIP configuration. I set the AD 100. I went under the OSPF configuration. I set the same AD 100. And same for EIGRP. Now this router, to go to this destination, which protocol it will choose? Because remember, considering same CIDR, same 2424, CIDR is same. So I remember like CIDR is same, then what? AD is same, then what? Metric. You cannot compare metric protocols. This criteria is not even applicable. So the only thing that is left is what? So will it do that? Or okay, so once, like when you revise the videos, whatever questions I ask, you can note it down somewhere, so that at the end, when we are done at the end, we are at the end of the session, we can discuss all those questions. You can try to find the answer for this question. Answer is very simple actually. Okay. Most probably throughout the content we will discuss it, but you can find the answer to this question by yourself. Otherwise, at the very end, when you remind me that these were the questions that we did not discuss, we can talk about it. Okay. Fine. Now, when it comes to the routing process, like we have this topology, like we have PC1. This is the topology that we will be using to understand the routing process. So we have a PC1, we have a server, we have two routers. In between these two routers, we have a serial cable. And here we have the Ethernet cable. The IP addresses and MAC addresses are, represented here. One thing that you notice on the serial interface, you do not see the MAC address, because on the serial interfaces, there are no MAC addresses. Serial interfaces are considered as a point-to-point interfaces, and Ethernet technology is considered as a multi-access technology. That means I can use an Ethernet switch and I can connect multiple devices at the same time. So if I had to send the traffic from one device to other, some unique ID has to be there, some unique addressing has to be there. And that is what MAC address does. MAC address provides a unique identification for the devices in a local area network. Now, serial technology is considered, it is considered as a point-to-point technology. And what do we mean by point-to-point technology? Is that we cannot even have this. We cannot have this. This is not even possible. Why? Because on the switches, we do not even have the serial port. So this is not even possible. It means that if we have connected two routers via serial cable, it is just a one-way path. Like if you exit from here, you will reach there. There is no other destinations in between. That means you do not need to uniquely identify the sender and receiver. It is just one way. If you board it from here, the plane will land on Delhi. There is no in between. So I do not need to uniquely identify the sender and the receiver. But let's say there were multiple destinations where the packet could go. In that case, I have to do that. In that case, I have to uniquely identify the sender and the receiver. And that is what MAC address does. MAC address is used to uniquely identify the sender and receiver in a local area network. Fine. So serial technologies, they do not have the MAC addresses. Ethernet technologies, we do have the MAC addresses. So we have MAC address, we have MAC address. Now, for this is what we call as a broadcast domain. This is a different broadcast domain, and this is a different broadcast domain. If I had to send the traffic within the broadcast domain, then it's okay. But if I had to send the traffic to another broadcast domain, I have to go to my default gateway. So remember, it's not the responsibility of the device to send the packet to the destination. It is the responsibility of the device to send the packet to the gateway. And default gateway will now look up the routing table, and then it will forward the packet towards the, what we call this as a next hop. This is what we call as next hop IP, and this is what we call as exit interface, self-exit interface. So from the PC point of view, the next hop is this one, default gateway. From the router point of view, to go there, this is the next hop. From this router point of view, this is the next hop. From this server point of view, this is the next hop. From this router point of view, this is the next hop. From this router point of view, this PC is the next hop. So if I am here, and if I have to go to 192.168.1.2, my next hop is what? Destination. Point I'm trying to make is that the next hop can be a router or it can be a destination itself. Think about it. Let's say you had to go from Pune to, let's say, Delhi. In between Pune to Delhi, there are multiple places where your train will stop. So your source, destination, and every intermediate stop is what we call as next stop. So when the train arrives here, the next stop is the destination. But when the train is here, the next stop is not destination. Next stop is another router or another stop. So from the PC point of view, next stop is gateway. From the router point of view, next stop is a router. From the PC point of view, next stop is a router. From the router point of view, next stop is a router. From this router point of view, to go to this destination, the next stop is destination. From the server point of view, to go to this destination, my next stop is router, next stop router, and next stop destination itself. Fine. Now I have my IP, I have source IP, I have destination IP. Remember, source IP and destination IP will not change throughout the path. This point is made very clear in your CCNA. But remember, source MAC address and the destination MAC address gets changed throughout the path. That is why we say MAC addresses are unique in a local broadcast domain or local area network. It is very much possible that whatever MAC address I have here, I have the same MAC address here. It does not matter, because if I have to send the traffic from this IP to this IP, this will be my source MAC address and this will be my destination MAC address, the MAC address of the default gateway. Once the packet arrives on the router and the packet crosses that broadcast domain, a new information is added. Remember, decapsulation, encapsulation. And once the new information is added, your old MAC addresses will be of no use. So it is completely possible that whatever MAC addresses are here can be here. So MAC addresses are worldwide unique. That's what we study. But their significance is only in a local area network. Whatever MAC address I have here, it has no significance on here. I can have, in fact, same MAC addresses on both the broadcast domains. It is possible. We can have this MAC address here and the same MAC address here as well. It is possible.
Same MAC?
It is possible. Because think about it. Now, if you have to go to this from this IP, if you have to go to this IP, your MAC address is only and only valid in this broadcast. So no. I'm not talking about from global internet or network point of view. I'm just talking about in this topology. In this topology, we can have the same.
Same MAC address, I'm talking about like million words.
No.
Device has
A unique MAC address. Yeah, I can change it now. I can change that.
you can change.
Like we can change the hard-coded MAC address to any MAC address that I want. I can do that. We'll do that. Whatever MAC address I have onto this machine, I can change it as per my requirement. That is what people
Like,
logically, physically is basically going to be same, whatever was burned in, but that will not be used. What will be used, that you change. Whatever you change it to, that will be used. It is possible. It is possible. It is not a, honestly, it is not a very big deal. It is possible. Just an example for the same. Anytime you connect to any Wi-Fi on on Android nowadays, it is always a random MAC address.
random MAC address of my
Mobile.
phone.
Exactly.
Generate
Exactly. Your device automatically generates a random MAC address every time you connect to any Wi-Fi, so that you do not have any attacks based on the MAC address. Security, exactly. So is it not possible that whatever, see, we have a fixed amount of MAC addresses. Is it not possible that your MAC address will be somewhere else? It is possible. Logically, obviously. Because see, you are not connected to internet directly, you are connected to router. So your MAC address is unique up to the router point, na? And after that, it could be anything. But if you exactly, if private IP addresses could be anywhere, it could be same. And if you connect like mobile data, if you connect to mobile data, in that case, it is the same MAC address. It is the actual MAC address. It is not random, because that is global. You will study throughout the content that we know about things, but we do not know that much. Like, for example, MAC address is not that much of a big deal. MAC address is just a small topic, but you will discover a few new things regarding the MAC addresses as well. Yeah, so that is exactly the thing. So we'll talk about this topology next. Like we'll implement this topology, and we will do the practical on this topology. Note that in the serial technology is not that commonly used in modern day network, because since the Ethernet standards have evolved so much that nowadays Ethernet is used as a WAN technology as well. But in earlier days, serial was very popular as a WAN technology. Ethernet was more popular as a LAN technology. And even the Ethernet standards that we used to have earlier, they had that limitation like 100 meters maximum. You can go up to 100 meters. But nowadays, since we have fiber opticals, we have coax. In older technologies, we had to add repeaters in between, like every 100 meters. But nowadays, we have that fiber optical technology where we do not require any repeater. We can go up to like 100 to 150 kilometers. That is 100 miles and more than that, without adding any repeater in between. So since the Ethernet standards have evolved so much that we can use the Ethernet as a WAN technology. In most of the network as a WAN, you will find the Ethernet. So serial technology is not that much popular. No. It is possible that the Ethernet, like using those fiber cables, like we can connect two locations that are 100-150 kilometers away without any issues, without any repeaters. Increases, yeah. Then in that case, you will add some repeaters or some other things, but up to 100-150 kilometers, you will not need any. That is the advantage of using the technologies such as fiber optical. And we have like single mode fiber, multi-mode fiber. These fiber optical technologies have that much like length, that much distance that they can cover using a single fiber optical cable. We will not require any other repeater or any other thing. So this topology I have already created. I will share with you this topology as well. And this is the basic topology that we will be using. Same thing, same thing, like one PC, one server, router, same topology. This is on GNS. All the topologies that I will give you will have IP addresses pre-configured. Like you do not have to configure the IP addresses. You just have to do routing, for example. So here also I have already configured the IP addresses. Here we have IP addresses configured here already. Instead of server, it is just a PC, so it does not matter. So the IP address is exactly the same: 192.168.1.2, 192.168.3.2, 1.1, 3.1, 2.1, 2.2. Everything is exactly the same. Just for the this MAC address that they have written here, this MAC address that they have written here, for example 1111, it is not possible to assign this MAC address. Okay, so I have changed the MAC address, just like I said in the last class that we can change the MAC address of the network interface card. The burn-in address will remain the same, but for the communication and everything, the MAC address that you have changed will be used. Yeah, in order to provide any like security based on those MAC address based attacks. So in that case. So if you see what I have done here, this PC, I have changed the MAC address of this PC. Like this PC on interface FA0. This is not a PC. Anytime I have to use a PC, what I do? I just take a router. So this is GNS3 interface. Okay. And here, like you will take I can have a PC. This is what we call VPCS, virtual PC services. So this is just a PC that I can take, but this is a Linux based PC. There are not a lot of commands and anything. So I generally do not use this. You can have your physical machine connected with this one as well. So you can have a VM. In the VM, you can have Windows machine installed and you can connect that VM with this host. That is possible. I'm not going to use that as well. Okay, so what I do generally, anytime I have to use any PC or any end device, what I do, I just take a router. A router I take, I will just right click, change, where is that? Change symbol. I will just change the symbol of this so that it looks like a PC. Okay, however, it is still the router. Changing the symbol is not going to do anything. So I'm going to rename it. For example, whatever name you want to give it, you can just double click. And once you power it on, you do what? You disable the routing. So if you disable the routing, it is no better than just the end device. So all these, no IP routing. I will just use the command no IP routing here. And by using the command no IP routing, I will disable the IP routing so that this device just acts as a end user, end device. And that is what I have done on here. On PC1, I have already done that. On PC2, I have already done that. This is not PC1, PC2. It is actually the router, but I have just changed the symbol of it and I have disabled the routing. So if you double click on that, the putty secure CRT, the session will open just like in a normal router. And you can just, I can just click here. I can use the command configure terminal, no IP routing and IP default gateway, because if I have disabled the routing, I have to set the default gateway. So how can we set the default gateway? IP default gateway command. And what is the IP address of the default gateway for that particular PC? 192.168.1. That's it. Yeah, default gateway is just normal. Default gateway is just IP. And I can say show IP route. If I say show IP route, I will see that routing is disabled, because otherwise I should have seen like routing table. So there is no routing table. This is just, it says that default gateway is this one. It indicates that you have disabled the routing and it is just next hop IP. This is just the default gateway. So anytime you have to use any end user, any PC, use just a simple router and disable the routing and do this. I can also connect my PC with GNS as well. It is possible. We will do that in IPv6 section. I will tell you how can you connect your PC with the GNS. Anyway, so this is what I have done on PC1 and this is what I have done on PC2. On PC2 as well, same thing. You say show IP route. You notice the gateway is set, which indicates that I have actually disabled the routing and it is just the default gateway. What else? On this interface, I have changed the MAC address of it as well. How can we change the MAC address of the interface? Just go under that interface. You must already be familiar with this command. You can just use the command MAC address and double B. Remember, MAC address is a hexadecimal. So AA, B, 0 to F, anything. AA, B, C, 00, and I will just call that 1002 because that is what I was asked to set here. So I'll change the MAC address. As soon as you change the MAC address, the link will go down and it will come up again. It will flap one time. Remember that this is the format that you have to use when you have to set the MAC address. It is not like those, not like this. Here, if on your Windows machine, if you see the format of the MAC address is something different. Like if you say get MAC, the format of the MAC address is something like that. But it's not exactly the same as the PC. On Cisco routers or on Cisco devices, the MAC address is written in this format. It will be used in the same hexadecimal colon notation, but here we have to write it down like that. One thing about the MAC address, the 8th bit of the MAC address should never be 1. So if you are setting the MAC address manually, you have to keep in mind that the 8th bit of the MAC address must not be 1. 8th bit of the MAC address must not be 1 in binary. So you convert this MAC address in binary. You convert this entire MAC address in binary. 8th bit of this MAC address from left to right, it should not be 1. Yeah, from the first. Yeah, exactly. Like this is the octet. So the 8th bit here, if you convert this in binary, the 8th bit must not be what? 1. Otherwise you will not. Let me show you. If I say the one that they say, like, you know, they say like configure the MAC address what 1111 1234 1234 1234. It will just not allow me to do that. There's a reason behind that. But at the moment we are not going to discuss that. We'll talk about that in the routing sections furthermore. But here, just remember, when you do this lab, in this lab we have to change the MAC address. Make sure that the MAC address is not having 8th bit as binary 1. Yeah, first, no, 8th bit, not the entire 8th bit. Like if I convert this in binary, it will be what? 1010 and 1010, no? So this one. Yeah, but in the first octet, lastmost bit must not be. Bit must not be 1. So this is like A, and this is also what? A. First octet. 1, yeah. 8th bit, which means like if you convert the entire MAC address into the binary, yeah, the least significant bit in the first octet must not be 1. Anyway, so I have changed that MAC address and everything. Fine. Okay. Now I am on router 1, and on router 1 I have given a route to reach to 192.168.3 subnet. I have done a static routing here. I go on router 1. On router 1, we will do static routing later on, but I hope you remember this. Show IP route static. This is how we can configure a static route. The command is show IP route. Like if I show you the command, show run. In the show run, you can use this output to validate what command I have used for the routing. So the command that I have used for the routing is this one: IP route destination network mask and what? Self exit interface. Which means that on router number 1, I have given the route to reach to 192.168.3, and on router number 2, I have given the route to reach to 192.168.1. On both the routers, I have configured the route. You see, because our focus here is not routing, our focus is here the routing process. So you can configure whatever protocol that you know. You know static routing, configure that. You know OSPF, configure that. All I need is the end-to-end reachability between these two devices. Now you can use like either static routing for the same, or you can use OSPF or whichever routing protocol you are familiar with. Okay, so static routing is much more easy. In a small scale network, I just had to use one command on router 1, and I had to use one command on router 2. It's okay. So I went for the static routing. Now I can ping. If I go from PC1, if I go from PC1 to PC2, I can say like ping 192.168.3.2, and I can see that the ping will be successful. If everything is correct, the ping will be successful. So a few packets got dropped, and then the ping was successful. Okay. Now we have to understand what is the background process of this. Like what is actually happening in the background. For that, we have to again go through the OSI model, the 7-layer, or the one that is actually implemented TCP/IP model, where originally we had 4 layers. Later on, they modified that, and modern day TCP/IP model has 5 layers. Okay. So here, I'm going to, when I say ping, and also what I'm going to do, see, I will right click here, right click, start capture. You click on that. So when you download this GNS and install, there is a tool that gets downloaded in the background automatically, which we call as Wireshark. This Wireshark tool is there to capture everything that goes onto the wire. So I have, enabled the Wireshark here as well, and I will enable the Wireshark here as well. Okay, I will enable the Wireshark here, and I will enable the Wireshark. I will capture the packets that are flowing out of that link on all three interfaces. Okay, now when I do ping from PC1 to PC2 end to end, I see a few messages here, like some messages are here. You can see few messages are here, few messages are here. So this is the first capture, like between PC1 and router 1. This here is the second capture right here. It is between router 1 and router 2. And this right here, like on the top, it is written here, router 1. You might not be able to notice it, but here it is written router 1 and router 2. And the third capture that I have here is this one, router 2 to PC2. So what happens that when we use this command on PC1, I use the command ping 192.168.3.2. Ping is not a protocol. Ping is more like a utility. Ping is more like a tool that network engineers use for connectivity testing. So if I had to check the connectivity between two devices, all I had to do is ping from one device to the other device. Ping is not a protocol. Ping uses ICMP protocol in the background for its operation. In fact, ping has a full form, packet internet grouper. This is the full form for ping. So ping is not just a protocol, it is just a utility, it is just a tool that we use for connectivity test. It is just a command that we use for connectivity testing. In the background, ping uses a protocol called ICMP, Internet Control Message Protocol. So whenever we use the ping process, whenever we use the ping process, it is going to use ICMP protocol for its operation. And in fact, ping has a reverse process called pong. So it is actually ping pong. It is ping, and the reply that comes, it is what we call as pong. So it is actually exactly the ping pong. They use the term ping pong from the sports. So the ping is a process that uses ICMP for its operation. ICMP or Internet Control Message Protocol is also used in IPv6 for something called Neighbor Discovery Protocol. Ping uses ICMP, and when you study IPv6, you will notice that there is something called Neighbor Discovery Protocol, NDP. It also uses the same ICMP protocol, but there we call that ICMP v6. So ICMP has two versions, ICMP version 4 and 6. ICMP for IPv4 and for IPv6. So ICMP v6 is there for IPv6 network, and ICMP is there for the IPv4 network. So ping is a process that uses ICMP for its operation. ICMP is also used in the Neighbor Discovery Protocol for IPv6, but there we call that ICMP v6. So when we ping from PC1 to server 1, in our case, when we ping from PC1 to PC2, if you want, you can change this to server, like you can change the symbol to server, it does not matter. So when we ping from PC to server, ping process at PC1 constructs an ICMP echo request packet. In ICMP, we have two major type of packet. For example, like in OSPF, we had 5 packets, hello, DVD, and all those. In similar way, ICMP has one packet called echo request, and ICMP has a packet called echo reply. ICMP echo request packet is the one that PC is going to send to check the connectivity, and the other end is going to reply with ICMP echo reply. So when we ping from the PC1 to server 1, ping process at PC1 constructs an ICMP echo request packet and sends it to the lower layer for further processing. Remember, ICMP is a network layer protocol. It works at layer 3 of the OSI model, which means if ICMP packet is generated, that ICMP packet will be handed over to network layer for further processing. There will not be any involvement of TCP, UDP or upper layer. So any protocol, if I say that OSPF is a network layer protocol, EIGRP is a network layer protocol, ICMP, IGMP, GRE, all these are network layer protocol. What do I mean by that? I mean that all these protocols are going to generate their packet and they will hand over that packet directly to network layer. There will not be any involvement of layer 4, layer 5 or beyond. So ICMP is going to generate an echo request packet and it will send that packet to network layer for further processing. In terms of TCP IP model, we call that layer as internet layer for further processing. And this is the ICMP packet header. We have a field in the ICMP packet called type. We have a field called code, checksum, and rest of the header. This is just like in OSPF we have packets. In ICMP we have the ICMP echo request packet, and the ICMP packet has this format. So any ICMP packet, if you open that ICMP packet, you will see these fields. What is this type field? Type field is used to tell if it is ICMP echo request or if it is echo reply. So if it is 8, if in the type field 8 number is written, it means that it is echo request. And if number 0 is written, it will be considered as an echo reply. So let's say the PC generates the ICMP packet. In that packet is an ICMP echo request packet. So in that packet, the type field is going to be automatically. Code is there for like error reporting. See, you must have seen that sometimes what happens, you ping some destination and you get destination network unreachable, destination host unreachable, these sort of error messages you get. How the machine knows that my ping packet got failed because of which error? So that is where code value comes from. So let's say I sent a packet was received by the router, and router is not having any route to reach to the destination. So router will send an error message to the host saying that destination network unreachable. I do not have any route to go there. So in that code, it will put some value looking at which the PC will understand there is an error. Point, no, see, if it is point, if it is here, like if it is, see, this point means that the packet got dropped somewhere. And unreachable means that the device is reporting that I do not know how to reach there. Maybe there are chances that the packet went to the router, or router did not has any route to reach to the destination, so router will say unreachable. In that case, you will see what but otherwise what you should see? Points. Point means that the router forwarded that and I do not know where the packet got dropped. Remember, think about it. If I'm saying that ICMP is a layer 3 packet, it means that ICMP is going to generate the packet and it is going to hand over that packet to layer 3 directly for further processing. Now think about it. If layer 4 is not involved, how the guaranteed delivery of the data will happen? Who takes the guarantee of TCP? There is no TCP. That means, remember the first line of in your CCNA workbook, the first line about IP is unreliable. It means that IP is not responsible. Network layer will encapsulate the packet, send it. It does not care if the packet gets delivered or not. Best effort delivery. Yeah. So that dot signifies, that dot means that the router forwarded that packet, it got dropped somewhere, it does not know where. And yeah, like UDP, exactly. So if you see U, it means someone is reporting that I cannot reach to the destination, unreachable. And dot means more like timeout, request timeout. I sent the packet, but I did not receive a reply within the time period. So I'm going to show it as dot dropped. See, ICMP echo request and echo reply, it has to have some time limit, na? Otherwise, I will send the echo request and I will wait for the reply for infinite time period. So there is a timeout, 2 seconds. If I send, for example, 2 seconds. So if let's say if on the machine there is a timeout of 2 seconds for ICMP operation to get complete, it means that the ICMP operation must get complete within 2 seconds. If it does not get complete within 2 seconds, I will do this what? Dot drop. Exactly.
But unreachable means it is like
Route missing, anything. Like the route is not there. In that case, you should see unreachability. There is no reachability from next hop. From the router, I do not know how to reach there. So a router sent an unreachable message to the host machine. Now, the checksum field is just for some sort of error detection, so that someone if modifies the ICMP echo request and sends it, so I should know about errors in the ICMP message. So for that we have that checksum field. Rest of the header field varies based on the content of the packet. It is not in the frame, it is inside that ICMP packet itself. That checksum is there in the Ethernet as well, but it is inside the ICMP packet itself. So on the data, it will calculate a checksum and put it in the checksum field. Yeah, inside the ICMP packet. Yeah. So this ICMP packet, which we are going to call as ICMP echo request packet, will be generated on the PC and it will be handed over to the network layer for further processing. If I show you this, how it looks like actually, so this is the first capture. Okay, I can just click on this, double click on this. If I double click on this, anyway, you can just see from here, it is what ICMP, it is what echo request, it is echo reply. You can get a lot of information from here itself, but if you double click on it, you can see this is the ICMP echo request packet. This is what type 8. Type 8 means echo request. Code 0 means no error. I will tell you the other codes as well in a moment. Checksum and that's it. Rest of the header field. Rest of the header field. This is the rest of the header field. It varies based on the data. I told you that ICMP is not only used in ping, it is used in some other things as well, such as NDP. So the field is going to vary based on that. So this like a sequence number, identifier, these things, these are going to vary. This field is there because we are sending just a ping packet, ICMP echo request packet. And the data is nothing like it is just 72 bytes of random bits, like any random number, whatever, it does not matter. This is 1, 2, 3 and the rest of the header. This is what we call as ICMP header, and this is what data. So I sent a packet which was an ICMP echo request packet. Now, what are these error codes? If you want to know about these error codes, for example, you can just look up ICMP on Wikipedia and you can just click on here and you scroll down a little bit, type code checksum. Checksum is calculated from the header and data. So the checksum is going like whatever data we are sending within that ICMP echo request packet and the header, content of the header, all will be used to calculate a value, which is what we are going to refer to as checksum. It will be used for, again, same like some sort of error checking, just like it is done in the data link layer header. Data link layer trailer. Now, The rest of the header field, it varies based on ICMP type and code. Now see, type 0 is what? Echo reply. Type 8 is what? Echo request. 6, 7, these like 15, 16, 17, deprecated, all like either these rest of the fields are experimental, unassigned, or not even used. What fields are actually used that we should worry about at this level? One is what? 0, one is what? 8, and the other one is this one. Let's say I have 1 and 2 is unassigned, like you will never see in the type 1 or 2. Now if the type is 3, just by looking at that, the device will know that there is an error. So if the type is 3, it means what? Destination unreachable. And why? Why the destination is unreachable? It is there in what? Code. So type 3, code 0 means a destination network unreachable. Type 3, code, see, type and code are two different fields, na? So type 3 and code 1 means what? Destination host unreachable. Type 3, code 2 means what? Destination protocol unreachable, port unreachable, fragment. These are the errors that the ICMP packet can report in the ICMP messages. 8 means what? Echo request used to what? Ping, and echo reply used into what? Ping.
But sometimes you put in protocol
That is okay.
To upper line.
Okay. That is okay.
In each case, for example, from router to PC, because we understand that on layers, you have to send it.
No, it is from see on the device, all these protocols are running in the background, all the processes are running in the background. So every time, let's say I open the command prompt and I said ping google.com, as soon as I hit enter, the ping process which is running on your machine is going to generate an ICMP echo request message. It is going to hand over that message to what? IP protocol. One thing you should be very clear, there is nothing like layers. Layers are not there. There is no 7 layer, there is no 5 layer. It is just for us. It is just for humans, for us, so that we can understand the data process properly. For machine, it is not there. Machines, let's say, if I have to, develop a protocol, I'm not going to tell that protocol that, okay, you are going to hand over your data to the network layer or transport layer. I'm going to say, this is the protocol, you will hand over your data to IP. That protocol does not care where the IP works, in the layer 3 or layer 4. It is for our understanding that if I say that the application program has donated the data, you immediately think of application layer. You say like the ping process has started the process, you immediately think of the layer 3, which is network layer. But for machine, it is not the case. So you should actually not understand it from the layers point of view. It's like ICMP protocol has generated a packet, it will hand over that packet to IP for further processing. Now the protocol does not care if that IP works on layer 3, layer 4, layer 10, it does not care. That is what we know, that IP works at which layer? Layer 3.
Yes, I understand. In case of protocol, there is sometimes, for example, you put CCNP. I know when you put like DCP or VPN, you have to
hand over, so
for example, session
okay,
connection.
I get it, So
But in case of
ICMP, so in case of ICMP, that protocol number field is going to be 1,
yes,
which means that it is just an indication. So when the receiver receives that data, it decapsulates the data, it checks the IP header. In the IP header, it finds what protocol number exactly what? 1. So what that indicates? It indicates that remove the IP header and hand over the packet to what? ICMP for further processing. It does not matter ICMP works at which layer for that machine. So ICMP, see, at one layer, data can come from the upper layer. This is what you know. And at a layer, data can be generated directly as well. It's not like the data will always come at the layer 3 from layer 4. I can have some protocols that generate the data at layer 3 directly. That OSPF, EIGRP, ICMP, IGMP, GRE. Exactly. So that is why when the packet arrives on here at layer 3, by looking at the protocol number, it is very clear that the packet has to be handed over to what? ICMP for further processing, and that's it. Machine does not care if ICMP works at layer 3, layer 4 or whatever. Just layer 3. It is for our understanding, because see, I do not see any TCP header over that ICMP. I do not see any UDP header over ICMP. So how can I say that ICMP is a layer 4 protocol? If ICMP was a layer 4 protocol, I should have seen the TCP header and the UDP header, na? But if I do not see that, what that implies, it implies that ICMP is not a layer 4 protocol. It is layer 3 protocol. Why? Because just after ICMP, what we see is an IP header directly. So yeah. So just by looking at the protocol number, packet will be handed over to the ICMP for further processing. The other layers such as TCP, UDP, they are not going to come in picture.
You said like after CCNP is directly IP header, right?
Huh?
Means there is like the ICMP encapsulate.
ICMP will be encapsulated directly in IP. You see now, you see, yeah, like that. You see now here, this is ICMP and directly what? IPv4. That means there is no TCP, there is no UDP in between. That means ICMP will be treated as what? A data. For what? IP. For IP, it is just the data that I have to encapsulate and send it to lower layer.
This is the data of
Layer for layer 3. Exactly. So right here, you don't have to memorize these. You do not have to memorize these. If you can, it is good, but you do not need to memorize these, because nowadays you can just always look up online for the codes. So you don't have to memorize these. Now, the ICMP packet will be encapsulated directly by IP. Now, either it can be IPv4 or it can be IPv6. So when the ICMP echo request packet comes at network layer, it will be encapsulated by network layer protocol. Now, earlier we used to have, apart from IP, we used to have other protocols as well, like IPX and AppleTalk. These protocols are what we call as legacy protocols nowadays, because you will not see these protocols in use in a modern day network. But remember that TCP/IP and OSI was not the only implementation of inter-networking models. There were other implementations of the inter-networking models as well. For example, we had something called IPX, SPX. We had NetBIOS for Microsoft. We had AppleTalk for Apple systems. This was, I believe, for Xerox. There was a company called Xerox, and they used to use this IPX or SPX. Either Xerox or I believe Novel Netware. Novel Netware, I believe. So they had a different set of protocol suite based on which they can connect their own devices and can send and receive the data. Before TCP/IP, OSI, and all these. So there, instead of IP, they used to use what? IPX. Apple devices, they used to use what? AppleTalk. IPX, Internet Packet Exchange, Sequential Packet Exchange. This is an older networking model that they had actually. But nowadays, IP is the only protocol. Yeah, you will not see, as I remember, you will not see these IPX and AppleTalk anywhere. In modern day network, you will not see these. but who knows, like in some company, maybe you might find some old machines or something like that. But I have not, personally, I have never seen in 8 to 10 years of my career, I have never seen this, like IPX or FLTop. So IP is the only protocol that is used by the network layer in TCP/IP protocol suite nowadays. Earlier, we used to have IPX and FLTop, but nowadays the IP is the only protocol that we will use. Now IP has two versions. One version is what we call IPv4 and one version is what IPv6. Since, see, when we did the ping, after the ping, did we write down IPv4 address or IPv6 address? IPv4 address. We said ping 192.168.3. So we have written an IPv4 address after the ping. That means IPv4 is being used. If I write like a ping and if I write like 2000 :1, then it means that IPv6 is going to be used. So based on if you are using IPv4 or IPv6, either your ICMP packet will be encapsulated by IPv4 or it will be encapsulated by IPv6. Since we are using IPv4, our data is going to be encapsulated by IPv4 at network layer. Now this is how IPv4 header looks like. This is the IPv4 header. Remember that this is the extra information that will be added over the data every time it passes the network layer. Any data that comes at the network layer will have this. How many bits? How many bytes? 20 bytes minimum, and maximum what? 60 bytes. It can go up to what? 60 bytes. You see, there is a field called options. So if you are using these option fields, if the header can go beyond 20 byte, it can go up to 60 bytes. So at least minimum 20 bytes will always be added over the data when it is being sent through the network layer. And what information is added? First information that is added is version. What this version field implies that is it IPv4 or IPv6? Since it is IPv4, it will always be what? 0, 1, 0, 0, which means it is IPv4. Next is what? IHL, we call that internet header length, or we call that just header length. What this field signifies? It means size of IPv4 header only, because IPv4 header can go from 20 to 60 bytes. So what is the size of the IPv4 header? It will be written here. Not exactly by converting 16 to binary and some different way, but this field effectively like it represents the size of the IPv4 header. Now type of service, why we use this field? We use this field for quality of service. So when we have to define some priority level for the packet at layer 3, we can use this field for quality of service. In the quality of service, we have like this is 8-bit, and 6 bits are what we call as a DSCP, and 2 bits are what we call as ECN. So this is what for congestion, and this is the priority. Yeah, marking and congestion. Then total length means the total size of the packet, header plus what? Data. Now let's talk about this field for a moment. What is the size of this total length? If you count, you will notice the size of this field is 16 bits. This is half. This is actually half. This is 16 and this is 16. So the size of the total length is what? 16 bits field. And using 16 bits, what is the smallest number that you can create in binary? The smallest number that you can create using the 16-bit is 0. How? Like you put all the 16 bits, like this is 16 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 16. I put all the 16 bits to 0, I will get what? The smallest number, which is what? 0. And if I put all these 16 bits to what? 1, I will get all the highest possible number. So you convert this 16 number of ones in decimal, you will notice that the result will come to be 65535. This is basically 2 to the power 16. 2 raised to the power 16 is the highest possible number that you will get. 2 raised to the power 16 means 65536. If you start from 0, it will be from 0 to 65535 bytes. Data and header in combined. Only data and header. Only data and header. So remember, our ICMP packet had how much amount of data? 72 bytes plus 8 byte for ICMP header. This is data inside that ICMP, and this is the header ICMP. Total what? 80 byte. This is all data ICMP plus what? Let us consider 20 byte for IP header. So it will be how much? 100 bytes. And what is this? So that the ping process that you do from the router here, even on the real devices, how much, like what is the size of the IP packet that will be generated in that ping is 100 bytes. However, if you do the same from PC, it will be 32 bytes only. So this size varies. I can change that size as well, but this size varies. Anyway, now what I'm saying, this total length field is what? 65535 bytes. Like, which this is just a number like 65535, which means that at max one IP packet can carry maximum how much amount of data in total? How much? 65535. That is the maximum limit for a single IP packet, including the header. So 20 byte for header, and the rest is all going to be what? Data. What is 65535 bytes? It is hardly 65 KB kilobytes. So I am saying that if you are uploading 1 GB data or even 1 MB data, 1 MB image file, whatever, that 1 MB image file is going to be like, it cannot be sent as it is. It will be chopped down, it will be, divided into smaller parts, and then it will be sent through the media. And every part can be maximum of how much length? 65535. It includes what? 20 byte for header and data, remaining data.
You know that the maximum size of frame is 1500.
Yeah. That limit is not going to be applied where? At the network layer. Not at least at the moment.
Because we are, this limit is beyond.
Wait. At the moment we are at data link layer only. Forget about MQ. Forget about data link layer. At the moment we are at which layer? At the moment we are at layer 3. Layer 3 is what? IP. I'm just saying that network layer can have maximum to maximum how much data? 65535 bytes in one packet. When the data goes to where? The data link layer, then we will see what will happen.
Yes.
But for the network layer, this is the limit. Once we go through the data link layer, it will be clear. But at the moment, we have to. We will see that at the data link layer, nothing like segmentation, fragmentation, it does not happen. at the data link layer. There is no such concept for the data link layer. We'll talk about that just in a moment.
So what confused me is like it's not like it's
That is okay. That means that which just means that network layer can generate. I did not say network layer will generate. I said network layer can generate the data maximum to maximum how much? 65535 bytes, which includes what? 20 byte long header and plus rest of what? Data. But I did not say that it is the actual limit. I said this is the maximum limit. Let me recall you now, since we are talking about the data link layer for a moment. Let me recall you, when you are doing the CCNA, you must have seen that MTU also varies from technology to technology. What about hyperchannel, where we have 65535 limit? There is a technology called hyperchannel. There, the MTU is not 1500. There is what? 65535.
it's like the same.
Yeah, it is. So the point is, the MTU that we know, it is on where? Ethernet technology. There could be technologies beyond that. See, network layer is not dependent on the media. But again, one more point for the CCNA. IP is media independent. I can use whatever media I want to use at the data link layer. So IP does not care about that. Network layer can generate the packet maximum to maximum of how much size? 65535 bytes. My question is, 65535 bytes hardly means 65 KB. What if the size of data is larger than that length? Maybe I have sent a 10 MB file. 10 MB means 10,000 KB. And all I know that maximum to maximum 65 KB can be transmitted in one packet, including the header as well. No, not buffered. So remember, in the transport layer, we have a functionality called segmentation. In the transport layer, we had the functionality called segmentation, where transport layer is going to divide a large segment into smaller, large data into smaller chunks. We call them segments. Let me recall you. There also the limit is what? 65535. Exactly. If you open the UDP header from your CCNA book, you notice that the total length is what? 65535. Yeah, in the UDP header. If you open the TCP header, there is a field called window size. 16-bit field is going to give you the number exactly the same, what? 65535. Not beyond that. Not in CCNP at least. But there are things that we will study someday later, but not at this level. Okay. So the point is, if I am sending like more than that much amount of data, network layer has a similar process. Like segmentation, network layer also has a similar process that we call fragmentation. Fragmentation is the same as segmentation. One happens at the transport layer and one happens at the network layer. And to support the fragmentation is the same process. Divide the large IP packet into smaller fragments. To support the fragmentation, these are three fields: identification, flag, and what? Fragment offset. These three fields are there to support something called fragmentation. So let's say I have two data stream. This is data stream number 1. This is data stream number 2, maybe one YouTube and one Facebook. We have two data stream, and for both the data streams, or maybe Google Drive, I'm watching a video and I'm uploading a file at the same time. So let's say there are two data streams, and for these two data streams, the data has to be divided into smaller what? Fragments. How the receiver will know this fragment belongs to which data stream? It must not happen that if your YouTube, or if you are uploading a file maybe in the fragments, that must not happen that it should like that interrupts your YouTube stream, something like that. So it must not happen. So that is why like the receivers must know how this fragment is different from this fragment. So I have received two fragment. This fragment belongs to which data stream? This fragment belongs to which data stream? Just to give an indication, just to give a hint about that, we have a field called identification. It is just a number, just any number, you see right here. Now we are talking about network layer. See, whatever, like any number, 0x0005. So if I send a large amount of data, every fragment will have the same number, which means that they all belongs to the same data stream. For other like Facebook or some other, this number will be different. Okay, fine. Then what? Then we have a field, see, version 4, header length, okay, 20 bytes, DSCP, ECN, which is what we call as quality of service. This is type of service. And then what? Total length, 100 bytes. Then identification, and then what? Flag. In the flag, we have 3 bits. First bit is always reserved. Second bit is called DF, or do not fragment, this D. Let's say you want to send the data and you do not want to fragment it. No matter what happens, I do not care if my data is delivered or not, but fragmentation must not happen. So I can send the data with a flag on, just like we had a SYN flag. So we can send the data with this do not fragment flag on. Means I have indicated the devices not to fragment this data no matter what happens. We can do that. See, ping. Okay, if I say ping google.com, for example, normally it will just be successful. And how much data it is sending? 32 bytes of data. It is not that big. IP can send what, 65535 bytes amount of data, and how much data we are sending in a ping? Only 32 bytes, which is, we do not require any fragmentation. But it is less than less than 65535. This is PC. This is PC. From my PC I am sending the ping, and my PC is using only 32 bytes for the ping. Routers, they use what, 100 bytes for the ping. So if I say ping google.com, and I can increase the size -L, and I can increase it what, 1000. So now what, 1000. That means now my ICMP packet will have the size what, 1000 bytes. Fragmented now, because the maximum limit is what, 65535. Let's say I do not want, let's say I am sending the data above that limit, 70,000. I know that this machine is not going to support that much actually. But anyway, if I send 70,000 bytes of data beyond 65535, I'm pretty sure that it will not support it. And I do not want to fragment it. So if you do not want to fragment it, what you can do, you can use the keyword -F. It means what? Don't fragment it. That means I just have to use the same. I will use, it will not support it, okay? But anyway, -this and what, -F. The maximum limit in this PC is how much? 65500. But anyway, I can do it from my router if I want to send. I can set the length. We'll talk about that. But that happens. But what I'm trying to say, that we can send the data with DF flag 1 or DF bit 1, which is just an indication that I do not want to fragment my data no matter what happens. If 0, it means that you can fragment, and if 1 means do not fragment. Now the last most bit is what? M bit. M. Flag means more fragments are to come. So if I send the data, and the data has been divided into 5 fragments. In the first fragment, M bit equal to 1, which means more fragments are following. So in here also M bit equal to 1, in here also M bit equal to 1, in here also M bit equal to 1, and here the M bit is going to be 0, which means that this is what? The last fragment. M bit means are there any more fragments or not? So M means more. So more fragment or not? This fragment offset field defines the, see, I sent a fragment. I sent the data and the data was divided into 10 fragments. How will I know that where to place which fragment? Because sequencing in the transport layer, how it is going to be done here? I do not see any sequence number field here. So if the fragmentation happens, how sequencing will be done for those fragments? So for that we have that field called fragment offset. Sorry? For the rearranging of the fragments that I have received, maybe out of order, out of sequence. So if you receive any fragments out of sequence, you should be able to rearrange it as per the original one. So for that we have that field called fragment offset. It is not the sequence number. It does not work like the sequence number. Someday we will talk about that, but for now just understand that this fragment offset field is to rearrange the fragments in a correct sequence. On the receiver side, because sender is going to fragment it. When the sender sends the data and it has fragmented the data, let's say into 5 parts, it will have fragment offset, fragment offset, fragment offset, fragment offset, fragment offset. It will set some fragment offset here, which will be an indication for the receiver that even if you receive these fragments out of sequence, you will rearrange them. Just like the sequence number, not exactly the sequence number. Keep in mind. Yeah. So just for the reliable delivery. Here there is no reliable delivery. If the fragment drops, if let's say any fragment gets dropped, it will be dropped. There is no reliability of IP to ensure that guaranteed delivery. So who will be responsible to ensure the guaranteed delivery of the data? Let's say I am using a protocol that does not use TCP or UDP. Then who will be responsible to ensure the guaranteed delivery of the data? No, the protocol itself. For example, I am using OSPF. My OSPF packet got encapsulated with IP. Now I know that my OSPF packet can get dropped, and I know that IP will not do anything about it. So it is the responsibility of OSPF itself to do something about that. So it is like whatever protocols that hand over the data directly to the network layer, they will have some mechanism to deal with the loss, but IP will not do anything even in that case.
For example,
DVD link state request click. Yeah. So it will take some time. We'll try to clear as much as possible. Now TTL, time to live. It is like for how many hops this packet is valid. See, TTL, time to live, it is in seconds actually. So this TTL field means for how long the packet is valid in the network. This is in second. This field is in second, and it starts from 255. 255, when the packet crosses the router, it will be decremented by what? 1, because it will be considered as 1 hop. See, modern day routers, even in the older time, the routers or the layer 3 devices that we have, they can receive a packet on one interface and they can switch it out of the other interface within 1 second. They can do that. They are that much capable. Let me just do a general calculation and you will understand. If I say, think about it. If I say this interface is fast Ethernet interface, what do you mean by that? What do we mean by that interface is a fast Ethernet interface? We mean that this interface can send the data at 100 MB per second. It can send the data and it can receive the data at the same rate, because modern day networks are full duplex. We can send and receive at the same time. What is this 100 MB in packets? Let's calculate this. in packets. So 100 MB means what? 100,000 kbps, 1000 bits per second. 100 MB means 100,000 bits per second. If I divide it by 8, I will get what? Bytes per second. If I divide it by what? 1500, considering that in Ethernet technology, 1500 byte means what? One packet. So let me do the calculation. 100,000 divide by how much? 8 divide by how much? 1500. Because see, I got that bytes per second, and if I divide by 1500, it will be how much? 8333 packets per second. So actually 100 Mbps means what? 8333 packets per second. It means that if this interface is that much capable, it can handle per second how many packets? 8333. So think about one packet. Modern day routers, modern day devices are capable of switching the packet on, like from one interface to other interface within 1 second, or even in less than 1 second, some in microsecond maybe. So it is not going to take 1 second in total for one packet to go from one interface to the other interface, but still TTL will always be decremented by 1. Yeah, it means that if I receive the packet on this interface and I have to send that packet out of this interface, it will be one hop, na? Yeah, because see, this is one network, this is another network. So when the packet crosses the network, it will be what? One hop. So we are sending the packet from one interface to the other interface, which is just a way of saying the packet has crossed a hop. No. See, hop means that the packet arrived on one interface and it went on the other interface. Then it will be considered as an hop. If you ping from the router itself, it will not be an hop because the packet will be generated by the router itself. Then hop will be like arrive and exit. But anyway, this TTL field is in seconds. It defines like how long the packet is valid in the network. But since modern day network can handle every packet, like they can switch the packet from one interface to the interface within 1 second. So this field generally, like we decrement this field only by 1, no matter how long it takes for the router to switch the packet from one interface to the other interface. They can do it within 1 second or they can take more than 1 second. I do not care. TTL will always be decremented by how much? 1 every time the packet crosses the router. Now, why we have this field? Why we have this TTL field in the packet? Exactly. So I want that my packet, if it gets stuck in the loop, the packet must not get flooded in the loop like for undefined time period. So I want that packet to get dropped automatically after some time. So for that we have the field called TTL. Remember, TTL is not there for loop prevention. Some people say TTL is for loop prevention. It is not the case. TTL is not going to avoid the loop. It is not for loop avoidance. TTL field just ensures that your packet will not loop around the network endlessly. But remember, if you did some misconfiguration between, let's say, these routers, you did some misconfigurations, okay? You did some misconfiguration, and because of that misconfiguration, a loop has occurred. When the packet arrives, the packet will get stuck in that loop for undefined time period. Again and again and again. TTL will just do what? After some time period, that packet will get dropped automatically, but loop is still there. So TTL field is not for the loop avoidance, keep that in mind. TTL field is just to ensure that the packet does not get looped around the network for undefined time period. Switches, yeah. No, it is not. In the routed network, the responsibility of loop avoidance is implemented in the protocol itself. So if you are doing the static routing, it is your responsibility that the loop must not be there. If you are using what? OSPF, it is the responsibility of which algorithm? SPF algorithm. If you are using what? IGRP, it is the responsibility of dual algorithm. So the best part, exactly, so that the packet does not get looped around the network. Okay. Source IP, destination IP, you already know. Source IP means from where the packet is coming, and the destination IP means where the packet is going actually. This, what is this protocol number? This protocol number means that what is being encapsulated, like this IP is encapsulating exactly what? Is this encapsulating ICMP, IGMP, EIGRP, OSPF, like GRE, what? So this IP, consider IP as a container, and what is inside that container is written on the top of it in the format of protocol number. So for example, if the protocol number is 1, it indicates that inside this IP, what we have is ICMP protocol. If I have what 2, it means what? IGMP. If I have 6, is what? TCP. If I have 17, it is what? If I have 47, it is what? GRE. If I have 88, it is what? EIGRP. If I have 89, it is what? OSPF, and so on. It is a 16-bit number, sorry, 8, not 16-bit actually, it is a 8-bit number. So 2 raised to the power 8 equal to 256, like from 0 to 255. So this protocol number is just an indication what is being encapsulated, or in other terms, what is the upper layer protocol, where I have to hand over that packet for further processing. Then we have header checksum to check for errors in header only. That is why we call header checksum. Remember, header checksum will be recalculated if any content of the header is changing. Let's say I received the packet and I sent that packet from this interface to this interface. That means my TTL will be decremented. And if the TTL will be decremented, that means the content of the header got changed and the device has to recalculate header checksum. See, think about it. On the PC, I generated an IP packet. While generating the IP packet, I calculated the header checksum using whatever algorithm. It came out to be 0xABCD based on the content of the header. Based on the content of the header, while sending the packet, I calculated the header checksum and it came out to be ABCD. Now, if the router sends that packet from one interface to other interface and the TTL gets decremented by 1, that means the content of the header has changed. And if the content of the header has changed, that means you have to recompute the header checksum. Otherwise, when the receiver receives it, it calculates the header checksum again, there will be a different value and it will drop it. So anytime there is a change in the content of the header checksum will be recalculated. 1, you will find what? TTL getting changed. Tell me any more example for the same. Any more example that you can think of where the content of the header will be changed. Take a look at the content of the header and give me one example where you think that the content of the header can get changed. No, you have already done it in CCNA. Neeraj, you can use the chat box, or you can raise hand so I can unmute you from my side, just in case if you have the answer to that. What about NAT? When you do the NAT, what happens? In case of NAT, what? Of what? IP, source IP, na? So if you change the IP, that means the content of the header will get changed, and what? The header checksum has to be what? Recalculated. So what I'm saying, that there could be conditions where the header checksum has to be recalculated. And if it does not get recalculated, there are chances that the receiver will drop that packet. Fine. So this is the extra information that will be added. And you see this extra information right here in the packet capture. Here, you see all that information here. You see it is 1. Why it is 1? Because ICMP is being encapsulated. Okay. Source IP, destination IP. Now you see these in brackets. This is not, this field is not there in the real packet. It is only in this packet tracer, in this Wireshark tool. Anything that you see in between these brackets, immediately think they are not there. They are just in the Wireshark packet capture. Fine. So version will always be what? 4, which is 0x, sorry, which is 0110100 in binary. Total length is the total size of the data, including the header. TTL, number of hops this packet can cross. Usually it is what? 255. Protocol number defines what is being encapsulated, ICMP, IGMP, GRE, and so on. And header checksum for a consistency check or error detection. Source IP, destination IP. In our case, my packet is going from 192.168.1.2 to 192.168.3.2. So my source IP will be 1.2 and destination IP will be 3.2. You see here in the capture. So now, like a lot of other information is present in the IP header as well, such as fragmentation. So if the packet has been fragmented, that information is there in the IP header itself. It is useless until the fragmentation has happened. So if the fragmentation has not happened, that field is useless. They are using that field for no reason again and again. I am sending 100 bytes of data. That data has not, that data we do not need to fragment it. But still that field is there. Those 3 fields are there. Quality of service, I have not even done any marking, but still that field is there. For no reason they have those fields, even though, so there should have been some mechanism. There should have been some mechanism, like when fragmentation is required, we will use that field. When the quality of service is required, we will use that field, but there is no such mechanism in IPv4. Those fields will always be there. It does not matter if the fragmentation has happened or not. It does not matter if IPv, like if we are using the quality of service or not. Those fields will always be there. So now the data will look like something like this. ICMP encapsulated with what? IP header. This is what we call as what? A packet. The data link at the data link layer, encapsulated data is what we call as packet. This is what we call PDU of the network layer, not the data link layer, network layer. It is what we call packet is the PDU, protocol data unit of network layer. Now from the network layer, the data will go where? To the data link layer for further processing, where the data link layer will add some header and trailer information. Now before going to the data link layer, let's take a quick look at the IPv6 header. This is how the IPv6 header looks like. Version is going to be what? 6. Traffic class is what? Type of service. Payload length is what? Total length. Next header is what? Protocol number. Hop limit is what? TTL. IPv6 also can categorize different flow of the data, and it can identify it by a number that we call as flow label. We'll talk about that in IPv6 section later on. But remember that in IPv6 there is a new field called flow label. This field is not there in IPv4. So some fields are as it is, and some fields have been renamed in IPv6. and one field is completely new. That is what we call a PLA. Whatever fields were off, whatever field we were not using, those fields are removed. Fragmentation and the other fields which are not required. I'm not saying that the fragmentation will not happen in IPv6. It will happen, but when that happens, we will use what? This is the fixed header. How much? 40 byte. Plus, if the fragmentation happens, we will use what? Extension headers. So 20 byte is for what? IPv4, and 40 byte is for what? IPv6. It can go from 20 to 60 byte if IP options are used. I can show you them just in a moment. I will show you. So let me show you some more things. For example, about the fragmentation, or okay, just we'll talk about that just in a moment. So this slide we should cover as well. Now at the network layer itself, the PC, the sender, will check based on the source IP and the destination IP. The sender will also check what is the next hop of this packet. Remember, in the last class we talked about that the next hop can either be a router or it can be a destination directly. So based on the source IP and destination IP, next hop for this packet is also checked. If the source IP and destination IP belong to the same subnet, next hop is the destination itself. That means if the sender and receiver belong to the same subnet, I do not need to go to the gateway. I can send and receive the data directly. That means my next stop is destination directly. I do not need to go to the gateway. But if the source IP and destination IP belong to a different subnet, next stop is always going to be the gateway. Since in our case, source IP and destination IP are in different subnet, device will set the next hop to gateway IP address, which is what? 192.168.1.1, and it will send the packet to the next layer, which is what? Remember, the packet has not exit the device yet. This is just layer 3. Now, one more thing, if you notice, when I did the ping, where did I write the source IP? I just said ping this destination. Where is the source IP? I did not write the source IP, but I see the source IP in the capture. So remember, if you specify the source IP, then very good. But even if you do not specify the source IP, the device automatically chooses a source IP. How? Remember, to go to this destination, what is your next hop? Next hop is 192.168.1.1. To go to this default gateway, what is your exit interface? FA 0x0. If I have to go there, I actually have to stop here. And to stop here, I have to exit from here. That means this IP, machine will automatically choose as what? The source IP. If I had, let's say I had multiple interfaces here. One going towards router 3, one going towards router 4. They can lead us to a different network like force network, 192.168.10s, whatever. If I have to go to 192.168.3.2, I have to exit out of this interface. So the IP address of exit interface towards the next hop will be used as the source IP address. So here if you see, in our case, if you do not define the source IP address while sending the packet, it automatically defines the source IP. And what is this? It is the IP address of the exit interface towards the next hop. And remember, if the default gateway IP you have not set, the packet will be dropped because the machine does not know how to exit outside the broadcast domain by default. So if you have set the default gateway, then only packet can leave from your local broadcast domain to somewhere else. But if you have not defined the default gateway, it just cannot happen. So default gateway you have to set, otherwise the device will drop the packet. And you do not see the IP address of the default gateway here. Nowhere you see that IP address of the default gateway. It is just the machine knows that if I have to go there, I have to go to this next hop. Actually, also note that the default gateway information is not mentioned anywhere in the IP packet itself. It is just one thing that the device knows. Now the data will come to the data link layer. At the data link layer, it will be checked which protocol will get to process that data. Remember, at the data link layer, based on the media, if you are using Ethernet, there will be what? ARPA protocol, Advanced Research and Project Agency. This is the name of the so ARPA network. They created a protocol called ARPA, which is responsible to add the Ethernet header, Ethernet trailer onto the data. So the name of the protocol is ARPA, and what it does, it adds the Ethernet header and the Ethernet trailer onto the data. And if we are using what? Serial, it will be what? SDLC, PPP, and frame relay. So what we are using? We are talking about PC1. From the PC1 to the router, what technology we are using? Ethernet in our example. So who will encapsulate the data? ARPA will encapsulate the data at the data link layer. Here, I can show you that. On the PC, show interface fast Ethernet 0x0. Not this one. This one. It is same, but this one. Encapsulation ARPA. It means that any packet that exits out of the interface FA0x0 will be encapsulated by Advanced Research and Project Agency ARPA protocol. And ARPA is going to add the Ethernet header and the Ethernet trailer over the data. Now in our topology, we have also used the switch. It is not having any significance in this topology. It is just to connect multiple devices in the same broadcast domain. That's it. Same VLAN, VLAN 1, VLAN 1. It is also set on the default configuration. We basically have not done anything on that switch. Note that the switch has no role other than just to connect the routers with multiple devices in the LAN, and it is set on the default configuration. So we have not done anything on the switch. Switch is just to connect multiple routers, multiple devices into the same broadcast domain. So now the packet will arrive at the data link layer, and this is well known data link layer header and trailer. So this is the packet that we have received from where? Upper layer, which is what? Network layer, and this is what? Header, and this is what? Trailer. In the trailer field is called what? FCS, frame check sequence, which is just the 32-bit CRC, cyclic redundancy check value. So the data link layer trailer, in the data link layer trailer, there is a field called like FCS. This FCS field is used to perform error detection onto the data. The device, while sending the data, will calculate FCS using the algorithm called CRC, and it will put that value on here. It's like this is the data that I want to send, this is the CRC algorithm, and this is the FCS. I will put this FCS here, and I will put this data here, and I will send it. On the receiver, when the data is received, let's say something has changed, the same algorithm CRC, because algorithm will not change, CRC is same, so the same algorithm will run, and the result will be compared with what is there in the FCS field. And since both the results are different, the receiver will assume that there is an error and it will just drop that frame. And it happens every time, every frame, any frame is received onto the device. Now the header, coming to the header, we have the field called what? Source MAC address, which is the MAC address of exit interface. Like if I'm sending the packet out of the interface FS0 that will be what? The source MAC address. Destination MAC address, remember, do not get confused with destination MAC address. It is not destination MAC address. It is the MAC address of next hop. Because your destination is not your next hop. Your destination is 192.168.3.2, but your next hop is router. So you do not have to add the MAC address of 192.168.3.2. You have to add the MAC address of router. Otherwise, router will not accept it. So always remember, destination MAC address is not the MAC address of the destination. It is the MAC address of next hop. And what is next hop for this IP packet? Device already knows from the previous layer. From the network layer, it was clear that if the packet is going from 1.1 or 1.2 to what? 3.2, the next hop is what? 192.168.1.1. And to go to 192.168.1.1, what is the MAC address? If you know, it's fine. If you do not know, use what? ARP. We'll talk about that. But destination MAC address is the MAC address of the next hop. And what is next hop for this packet? It is already known from the layer 3, previous layer. Source MAC address is your own MAC address. MAC address of the exit interface being used to send the data. .1q tag is used in trunking, if you remember. Here we do not have any trunking. I'm not going to do any trunk on my PC. So there will not be any 802.1q trunk, .1q trunk information. Yeah, exactly. So anyway, the data that PC sends is not going to be tagged. So this field is just, that is why this field is what? Optional. Ether type field has the same significance as protocol number. Remember, protocol number says what? What is being encapsulated? Now think about it. At the data link layer, IPv4 packet can come. At the data link layer, IPv6 packet can also be encapsulated. So what is being encapsulated? IPv4 or IPv6? When the receiver receives the frame, receiver has to forward that frame to IPv4 or IPv6. It has to be clear, and it is clear with the help of what? Ether type field. So while sending the data, sender will add the type 0x0800 if it is what? IPv4. It will automatically add this if it is what? ARP, and it will automatically add this if it is what? IPv6. It is used to tell what is being encapsulated by ARPA at data link. FCS is for what? Error detection using something called CRC. Now comes to the point. Now let's come to the point. The MTU. Payload could be 1500 bytes maximum in the Ethernet technology. Here. Now let's talk about that limit. In the Ethernet technology, the payload is maximum to maximum how much? 1500 bytes. That means the data link layer, at the data link layer, the Ethernet technology or Ethernet frame can carry maximum 1500 bytes of data. Then what? 4 byte for trailer and 6 plus 6 plus 2, 14 byte for header. So total frame is going to be how long? 18 byte, including the header and trailer. And if you add these 4 byte optional field, it will be what? 22 bytes. So remember, the size of the frame means like data plus header and trailer. Now the same question. What if at the data link layer, remember I told you that network layer can generate how much amount of data at max? 65535 bytes, which includes the header and what? Data. Anyway, if I combine in total, it could be maximum what? 65535 bytes. It means that the network layer can give maximum to maximum 65535 bytes amount of data to the data link layer. Now at the data link layer, the maximum limit is only what? 1500. What was happening at the network layer? Fragmentation. What was happening at the transport layer? Segmentation. What will happen at the data link layer to deal with that large amount of data? So if the size of data, question again the same, if the size of the data is greater than this limit, how the data link layer will deal with it? If you say segmentation, it is incorrect because it is done at transport layer. If you say fragmentation, that is incorrect because it is done at the network layer. No, data link layer will do nothing about it. It is not the responsibility of data link layer. Remember, we are talking about Ethernet technology. It is not the responsibility of data link layer to deal with the frames larger than that size. They will just drop it. It will just drop it. It does not care. Which means what? Exactly. This is why while performing the fragmentation, network layer, even though it is capable of fragmenting at this limit, it will not do that because it knows that ultimate bottleneck is what? You can have whatever data you want, but ultimately the bottleneck is how much? 1500 bytes. Network layer knows that the data link layer will not deal with the packet larger than that limit. So, and since the network layer knows that it is not the responsibility of the data link layer to do anything about that, it is the responsibility of network layer itself to do the fragmentation in such a way that nothing is required at the data link layer anymore. Like no fragmentation, no segmentation. Network layer should fragment it in such a way so that data link layer has to do nothing. It just has to encapsulate it with header trailer and pass it. Remember, in CCNA we have talked about same layer interaction and adjacent layer interaction. This is what? Adjacent layer interaction. Every layer, and more importantly, layers are not even there. So IP knows what? IP knows that at the data link layer, we say data link layer, but IP knows that, okay, media is what? Ethernet, and in Ethernet maximum limit MTU is what? So it will do what? Fragmentation based on what? 1500. Remember the original TCP IP model? There was only one layer. Physical, like the physical and data link layer, they were to merge together the network access layer. Exactly. And so it is exactly the same nowadays as well. We just, for our understanding, we divided that into two layers. So actually from the network layer, the data will get placed on the physical media. But in between of that, there will be something called a data link layer, which will be responsible to add header, trailer, source MAC address, destination MAC address, and all these things, and then pass it. So this is what we call as MTU, maximum transmission unit, which is what? Maximum amount of data that can be transmitted out of a physical media. In case of Ethernet, it is what? 1500. Now some Ethernet technology support something called jumbo frame yeah, jumbo frame. In the jumbo frame, this limit can go beyond 1500. Segment it accordingly. 9000 is a very common size of the MTU in a lot of switches, in a lot of devices. Okay. So this thing right here. Payload is what? 1500 bytes. So if the size of the packet is larger than that limit, what will happen? Fragmentation will happen at layer 3. Problem is, the device knows the source MAC address. I know my MAC address, but I do not know the destination MAC address, which is MAC address of the next hop. How this PC knows that I do not have the MAC address of destination? The PC maintains a table, a cache called what? ARP cache. The PC will check in its ARP cache. PC will look up the information in a cache memory, which maintains the IP address to MAC address mapping. And this cache is what we call as ARP cache, which is maintained by every Ethernet interface where we have configured the IP. So if there is an Ethernet interface and we have configured an IP on it, ARP cache will be there. ARP is going to maintain IP and MAC information onto that particular port. You can validate that ARP cache on the Windows machine by using the command ARP-A. If you use that command called ARP-A, all the interfaces that you have will be listed, and on every interface, IP MAC binding, IP MAC information will be listed as well. In the PC, in the routers, if you have to validate that, you can use the command show IP ARP. You can validate this command. So when I pinged for the first time, ARP process happened and I got the MAC address of the default gateway and I maintained it in a memory called ARP cache, and an entry in the ARP cache will be valid for 4 hours, so that you do not have to send the ARP request, ARP reply again and again. So it has been 72 minutes, which is like past 1 hour. This entry is valid for 4 hours by default. So the device is not having the destination MAC address. To know the destination MAC address, the device will send ARP request and ARP reply. Since the device is not having the information in the ARP cache, it will resolve the MAC address of the destination by sending the ARP request. We will talk about the ARP request. It will send the ARP request, you will get the ARP reply, then only you will encapsulate the packet and send it. And you see in the capture, in this capture here, I started the capture after the ping. That is why I do not see any ARP packet here. Otherwise, before this ICMP, I should have seen the ARP. We'll talk about that. So destination MAC address, this destination MAC address is MAC address of the next hop. If the next hop is default gateway, get that default gateway's MAC address by sending ARP request and ARP reply. If the destination is if the next hop is destination, get that device MAC address by sending the ARP request and ARP reply. If routing is enabled and every IP is configured, yes. If there is no layer 3 interface on the route, on the switch, there will not be any ARP cache. Okay. No. When we assign the VLANs and everything, if we configure a port into a specific VLAN, that port is still then what you have done? If you have configured an IP address to a VLAN, you have configured a layer 3 address onto that, na? So if the layer 3 comes into the picture, ARP will be there. Do routing. No issue. No issue. Even that switch can have the devices connected in the same network, na? It can have no issues. You can just configure an SVI yeah, interface VLAN, IP address, and you notice show IP ARP, you will see the ARP. ARP will always be there if there is a layer 3 interface. If there is any layer 3 interface, ARP will always be there.
But it will be after
ARP request, ARP. Like the device.
PC sends ARP automatically.
When we, let's say from the PC we generated a ping. If from the PC no packet is going, there will not be any ARP process. When the PC has to send something, then only ARP process will happen.
When you flag in PC the first time, PC have to know which device is in the RAM, right? There is some concepts.
We can say that. See,
This is ARP or no?
no, that is the other thing. See, point is if you have connected a PC onto your network, and that PC, will send variety of messages in the background. So, for example, Windows Update,
Yes.
Dropbox, Google Drive, Chrome, whatever applications are running by default on the PC, it will try to send the messages to those applications by default. Like for example, it will try to get Windows Update from the Windows server. To go to the Microsoft Windows, it will do a DNS resolution for Microsoft Windows. And for the DNS, it has to do what? ARP first. So by default, there is no such process. It is because your Windows machine is running n number of services in the background, because of which it has to do that. If your PC is sitting idle, no packets, I don't have to send anything from the PC, you will never see any ARP request, ARP reply in that case.
Otherwise, you will see.
Otherwise, like if the PC has to send anything to anywhere, you will notice ARP request and ARP reply. Even you can see here in this ARP cache, I do have only information about what? 3 things. 192.168.100.1, that is my gateway, and 2 more IP addresses here. This is router actually. This is the router to which I am connected. This is my default gateway. This is the router, and this I believe is some machine. There are other machines in my network as well, but I do not know their MAC address. When I ping, I will know their MAC address. So there is no default process like that.
These other addresses and MAC addresses for other things.
These
System.
These one.
Local, yes.
See, this is multicast. If you remember, 224. So yes, these are for
Multicast in local. There is an application running in the local.
there must be some application running on the machine itself, which is using multicasting. So for that it has this. So there must be some application 224. If you search that multicast address, you might find 224.0.0.22 being used for something. IGMP. It is for, so this machine, this means that my PC supports IGMP version 3. Same. These multicast MAC addresses must be reserved for something else. IGMP is different than ICMP. IGMP is for multicasting specifically. ICMP is for connectivity testing. So this thing here, the payload, and also let me just quickly show you the Ethernet frame, because you have to know the Ethernet frame as well. This right here, the Ethernet frame, remember, it is 6 bytes for destination MAC address, 6 bytes for the source MAC address, all that thing, and total size it was 61542. This is at layer 2 Ethernet frame. When the packet goes to the layer 1, in the beginning of that frame and in the end of the frame, some extra field is left at the data link, at the physical layer, at the physical layer. At the end, 12 byte gap is there in between 2 frames. 12 byte interpacket gap is there, and then preamble and SFD, which is 8 byte in total. 8 byte means 64 bits. It is all 101010101010. and at the very end 1 fix always. So preamble and SFD, they represent the beginning of a frame, that this frame is beginning, this frame is ending. So preamble and SFD, these two fields are at layer 1, not at layer 2. And you see here, where is that jumbo frame? You must see. Yeah, here. Minimum 42 and maximum 1500. So an Ethernet frame must have at least what, 42 bytes, and maximum is what, 1500. And jumbo frames, in some devices it is possible to send the data beyond the 1500 byte limit. Specifically how much? You see what, 9000 bytes. So this is what we call as jumbo frames. So some Ethernet standards, they support the jumbo frames as well, gigabit and all. In the gigabit technology, it is possible to send more than that much. Okay. So this is the data link layer header. Now we'll talk about the ARP process, and we will do the lab of this ARP